All right. Good morning, everyone. Welcome to day two of the 2025 OpenVSP Workshop. We're going to kick things off today again with Tim Kewitt from M4 Engineering talking about some of the new features with OpenVSP attributes, how those are used, how you can access them, and do a bit of a demo. So let's go ahead and get started. Tim, it's all yours.
Hey, thank you, Brandon, and good morning, everyone, to all who are watching. Thanks again for joining this stream to learn more about VSP. It's always nice to run into people whenever I can, even if it is just virtually this time. All right, so if anyone had attended last year's 2024 workshop, I gave a preliminary presentation on this work in progress concept called attributes. And this is a continuation of it as it has now entered OpenVSP's official releases. So we should probably have a little bit more attention to that just to explain the changes that have developed over time with it, as well as just the general concept of it, since this one is an online presentation and presumably many more people have access to watch this one. Right, so let's go on in for a bit. We're going to cover the attributes as a concept, the user interface that has been developed to support it, a few brief examples, and a demo of it. So, beginning with the concept, I'm sure people who have designed airplanes have come up with drawings such as this, where you just start jotting down your notes. You try to associate information with geometry or meta concepts, like what is the materials database we're using for this thing? What's the minimum gauge we'll be allowing for this fuselage, or how many ribs per wing? Or even like we have a section of this wing that has a special attention requirement in CFD because it has like a rubber boot for your de-icing. Or even just this airplane is not classified, things of that nature. Well, you might want to put this in OpenVSP now. So we make our airplane. And then we now represent that same information as attributes. This is the PowerPoint presentation text box, mind you, but same idea works. So we can make this information into notes of varying data types that's associated with various OpenVSP objects. And these notes are both readable by people and by API. So you can store it as notes for yourself or as information for other programs to read and interpret. So attributes really kind of a grease pencil of non-OpenVSP metadata. There are a wide array of attributable objects you can attach attributes to in OpenVSP, not just geoms, but any parm container, any parm. Well, yeah. And most of everything in OpenVSP is a parm or a parm container at its core. In addition, things like measures or sets or modes or even advanced links can all have attributes on them, as well as the vehicle itself at the highest level of abstraction. These are enabled with API and GUI for ease of use and to enable powerful integration with your analysis tools and design suites. And the initial release for this happened in OpenVSP 3.42.0 per a Phase 2 Navy-funded SBIR with M4 Engineering. Again, thank you, Navy, for the funding. It's been very nice to work on this, and we hope you're very happy with it. So we're going to continue into a little more detail here. So an attribute is, if you're used to, say, Python as a programming language, an attribute is similar to a dictionary entry. You have a name and you have a value. Except the type of value here can vary through a number of data types: strings, integers, doubles, booleans, matrices of doubles. You can even have groups of attributes. You can have links to parms as a sort of abstraction for accessing them, just in a similar way if you're getting a lot of information from attributes. But really, it's just, again, it's a name and it's a value. So you say, all right, I'm going to have an integer type attribute. I'm going to call it integer attribute example, and its data will be 55, an integer. And that's really the long and short of an attribute. It's quite a simple concept at its core. The integration, however, has a lot of implications, and you can do a lot of really powerful things with this when fully integrated. I think later today, Maxwell from M4 will be demonstrating some use of attributes in his example work. So stay tuned for that, of course. Moving on. So I'm going to have to trudge through some backend here. The attributes themselves live on what's called the heap, which is just a pile of computer memory that is static, known as non-volatile memory. So no matter what we do with the attributes, they're going to be safe. Meanwhile, the attribute collections may exist on objects that move around, or they might have vectors thereof. And essentially, we had to do a lot of overhaul of how some objects were stored in OpenVSP to make this safer to use. And the safety in using pointers means we have very lightweight objects that aren't nearly as clunky as they could have been, as well as managing a lot of abstract access to them. So attributes live on the heap. Attribute collections store pointers to the pointers, which are the memory addresses of these attributes. And attribute collections then live in OpenVSP objects. And an OpenVSP object could be a geom, it could be a measure, it could be the vehicle itself, it could be a parm, it could be a subsurface. And then lastly, we have the attribute manager, which manages all the pointers locations, as well as pointers to the collections, and centralizes all of the commands that involve attributes. So there's a lot of shuffling going on behind the scenes here, but we developed something that we think is fairly robust and effective. So let's look at some of the ways you might handle the GUI for attributes, because there's been a lot of new GUI features that I think anyone who's used OpenVSP has probably seen by now. So let's bring some light to that. So the main overview here is we essentially have two new big GUI features here. The first one you'll see is the Attribute Explorer, which you can open under the Model drop-down menu in the top bar of the OpenVSP. Or if you double-click on any of the attribute items in that Attribute Inline Explorer or Attribute Inline Editor, that will also open the Attribute Explorer to that attribute. So the Explorer is a vehicle-level tree, so you can just navigate the entire vehicle's set of attributes and attribute collections and quickly find which geometries, which objects have attributes and where and what they are. So they'll show the attribute name, its location in the vehicle, its value, and the data type all in the tree. And then on the right-hand side, we have the actual detailed data in case it runs over the short tab delineated version of the tree. We're going to look a little more closely at the tree in a minute. First, let's look at the attribute inline GUI. So this is attached to the bottom of supported objects GUI windows. So say the wing geometry or pod geometry. At the bottom of the Gen tab, you have the attributes for the whole geometry. And then in subsections like the subsurface, you may have subsurfaces in a geometry, and then if those are selected, you will see the attributes associated with that subsurface. So you notice in the right-hand side for the wing geom, we have a wing leading edge patch, and the attributes hierarchy here goes from the subsurfaces to the wing leading edge patch to the attributes collection of the wing's leading edge patch to the arrow mesh size double matrix attribute. Meanwhile, the pod geometry on the left simply just has the pod geom, and then the attribute collection for that pod geom, and then a double precision float attribute for the baggage volume, and then an integer attribute for the minimum skin gauge number of plies. So it's a quick way to preview the data inside of a single object. And again, double-clicking on any of those items in there will open the Attribute Explorer fully with the context of that item you clicked on. Meanwhile, the Global Attribute Explorer provides a top-down view of all the attributes in the model. There are nodes you can open and close in the GUI to make things a little easier to look around at, and it will only display the attribute collections that have attributes in them already, because every parm now has an attribute collection. And if we showed every parm at surface level, it would drive us to insanity. So there is one exception to that rule, in which if you have a GUI window open of any object, that object's attribute collection will show up in the Attribute Explorer, even if it is not populated. So you can use that to initialize and add attributes to empty collections. It makes more sense when you're using it. We can show that off in the demo a little bit. Further, we have cut, copy, paste, and delete controls in the bottom left. These can work for multiple selections, whether you're copying, cutting, pasting, or deleting. So you could cut multiple attributes, and then you could paste from that clipboard to multiple attribute collections. And this works both for attributes and groups of attributes, which we'll get into later. Sorry, the second thing to point out, of course, is the right-hand side. We have the detailed data screen for the attribute itself. This is a string data, and the strings support entire novels if you wish. You can put any data you want in there, although preferably something a human would read is probably the smartest thing to do for string data, but I'm not going to stop you if you want to do something really weird with it. Above the data screen, we have the add screen. You can select the attribute type and add an attribute, or you can add a group type attribute in case you want to create more hierarchical organization. And lastly, at the top left, we actually have a search bar. So if you're trying to find an attribute of a certain name, you can search by string. You can make that search case sensitive. You can search through any type of attribute, or you can search through any attributable object type as well if you want to down select further. So again, all of this is designed to empower you to figure out what the heck is going on in your model when you open it, because not everyone is the author of the model they're looking at, and frequently you might find something your coworkers made, or even something developed procedurally from a program. Okay, moving on to the second page for the Attribute Explorer. Here's an example of opening an empty attribute collection. So we have on the right a geometry I titled Some New Geometry, and that's being shown in the Attribute Explorer. On the left, it is a blank geom, and we have clicked on it in the geom browser. So its geom screen is open, and that triggers the GUI in the Attribute Explorer to then show Some New Geometry's attribute collection, even though it's empty. And this will work for multiple geometry selections as well. Okay, moving on. Right, I'm going to speed up a little bit here. Attributes support a variety of data types: booleans, ints, doubles, strings, matrices of ints and doubles, vector 3Ds, vectors of vector 3Ds, attribute groups, and parm references. Most of the GUI, the GUI is context sensitive. The Boolean has a simple push button you can click to turn true, false. The attributes for double matrices or int matrices actually have an Excel style spreadsheet widget that Rob built. And for the parm reference, that we actually get the same kind of parm picker we will see as from sets, modes, links, advanced links. And it even includes the slider, so you can drive the parm from this reference to a parm. Attribute groups are very powerful and important because it helps disambiguate similarly named attributes. So you might have multiple materials in your vehicle, and you're going to want to say Young's modulus or E every single time. So you could create an attribute group that says this is your aluminum material properties. Then you could put your E, your Poisson's ratio, your density, and any other string notes in there. Note that material or that attribute groups are actually shown in a magenta colored text, and any OpenVSP object that has a attribute in it is also highlighted in magenta and made bold. So when you're looking through at your parms, you'll see that. So we can see here, take a look at this pod geoms xform screen. We have 3 parms, xloc, yloc, and zloc. All 3 of these have an example attribute in them, and you can see that they are bold and purple. Meanwhile, the geometries, the pod geom and wing geom, have attributes, but the sum new geometry does not yet have an attribute. And again, if you're looking, you can use the search bar. Let's look at a few quick examples on how you might want to use an attribute. It's not going to be exhaustive because I want to save room for the demo. So we're going to look at vehicle level attributes. There are a few different interesting things specific to the vehicle. First, you can use it as normal. You can put any kind of attribute you want in there, but the vehicle itself in particular has default attributes that are built into the OpenVSP source code that are referenced in specific ways. And these 2 are watermark data and vehicle notes. And the vehicle notes gets an additional dedicated GUI window. The idea behind that is you could put a little blurb on the context for this model, and you can make that blurb open on vehicle open. So if you have that bool parm set to true, you open up this vehicle, the vehicle notes window opens with it immediately. So anyone opening it can see what you have for them to read. Then watermark data interacts with the render window to create a watermark. You can set the color alpha of the edge, the fill, and the text, as well as scaling the whole thing and setting whether you want it to be visible or not. This could be used for classification status, or even a hello world if you wanted to use it for other things. Moving on, a geom such as a wing, you might want to put the rib quantity in the wing as an integer. You might want to put the spar locations as a double matrix, or control surface deflections as a double attribute, or even minimum gauge layup information as a string. You might have a subsurf on a geom, and this subsurf might contain things like an arrow mesh size, in which you can store a double matrix of U and V mesh sizing seed for when you get to CFD, if you have a particular patch you're concerned about, for example. Advanced links also have their own attributes, and these will be found at the bottom of the advanced link window. And same thing can be done with measures, in which you might say, oh, I want to have the maximum allowable span for, say, a deck limitation. And last of the examples, we have parm references. Or no, not parm reference. This is an attribute on a parm. Important to keep that differentiated. So you might click on the parm for the mass over area of a geom here. So this mass over area might have a certain value, and you want to reference where you got the information from. In this case, we have the lightning protection structure that has to go on a composite layup, as well as a web link to where we got the data from. That's it for the attributable. That's it for the attributes examples. There are many more possibilities that exist. There's no time for a fully exhaustive set. So let's be smart and go to the demo for a minute. I'm going to stop sharing for 1 second while I get my VSP up, if that's okay. Cool. Okay, we are back. And we might notice a couple things here. First, the vehicle note screen, since this was set to true, it was opened when the vehicle was opened. We also have the watermark visible here. I'm going to move this to the left just so it's a little easier to see when we have other windows open. Okay, so let's cover some of the basics here. Let's say we want to have our new geometry here, and this is our blank, and we want to add an attribute to it. So you can't add them from here, But if you double click, that will open up the Attribute Explorer, and it contextually selects the same attribute collection that I double clicked on in some new geometry. Why don't we make a Boolean attribute? And this Boolean is plane flies in sky. Description, an example of a Boolean matter. Value true, thank goodness. Or we actually don't want that to be in attributes, we want it to be in a group that says general concepts matter group. And we want to put that in there. So we're going to cut that and paste. And you can use, of course, the hotkeys as well as the cut and paste buttons. The shortcuts are OS sensitive, so if you're using Apple, you'll see the proper command key, I believe. Rob, you can correct me if I'm wrong there, but I think it does that. Or we don't like where this is, so we're going to just get it out of some new geometry and put it in vehicles. And if you select the object or its base level attribute collection, it will paste to the same attribute collection. And there we go. General concepts adder group. So let's look at some of the vehicle level attributes. We have a map props group we made with some surrogate version of a basic Torre plane weave. We have aluminum. We can close those up here. You notice we have vehicle notes open here, and the string data for the vehicle notes is open here too. And when you see these grayed out screens here for the name and description, you'll know it's a protected core attribute that is interacted with in other ways in OpenVSP. And anything you want. Oh, right. This. If you want to put new lines in the string, you have to do Shift Enter. If you hit Enter, that is the data entry button. So just to know that. The other set of protected attributes are in the watermark group. So we have the toggle for showing and hiding the watermark. We can change the, say, fill alpha to half thickness, half fill, 20% full. The default fill color is a nice green per the Navy's request. I can make it a less nice green, but I like that. Make it big, make it small, make it normal. Okay, what's something else that is interesting? Another thing that's very interesting is if you go to a double matrix, add rows and delete rows, and what you notice here is that these rows are custom names. And that is one of those little tricks we've added in which if you create a comma delimited string attribute with the associated name of the double or integer matrix attribute, you can then create custom rows or column names, and it will go up to the end of that, and then it'll start doing blanks. Now, importantly, you can cut and paste from here, and it will fill in automatically to the new bounds of the matrix. And these can be cut and paste to and from your standard Excel type spreadsheet software. So not too much to worry about there. I would recommend against clicking add row and add call for tens of times, but it's good for filling in small amounts. Let's see, I'm trying to think if I forgot anything here. Let's say we want to copy an attribute to multiple places. Copy, paste. I'm going to hit Control C for that, and then I'm going to select multiple places. and paste it in multiple places. So now we have one here, here, and here. Again, a lot of work was done to make sure this is as intuitive and powerful as possible. Note also the close and open inactive nodes. So if I have these two selected, wing geom and some new geometry, and I close inactive nodes, then we just have some new geometry and wing geom open. So again, powerful way to open and close context sensitively for getting to what you want to look at. Or you can just open up everything. One thing that I think is at least a particularly fun flourish to look at is the parm reference attributes. So let's say we go to the wing geom. I'm going to add a parm type attribute. And since this uses the same parm picker code as the rest of OpenVSP, we could say drag the length of pod geom in here as an attribute, parm adder. And why you might want to do this is you might want to both get metadata and standard data out of your OpenVSP model through API to one of your aircraft design programs. Because you might just want length of this pod geom in addition to everything else. Because you might be storing metadata like baggage volume and minimum gauge, and you might just want to know how long this thing is too. Now the neat part is now we have control here, and it works the exact same as the original parm control up in the geom window. Anyways, I've probably rambled enough. I should leave some space open for questions. I was having a lot of fun over here. Let's see here. Acknowledgements. Thank you very much, Navy, for funding this under the Phase 2 SBIR from NavAir. It's been a very nice time working on this, and thank you all very much. Anyways.
Thanks a lot, Tim.
Yeah. You're welcome.
The stream lags about 15 seconds, so we'll give people a little bit of time to type any questions that they have into the stream. Andy Hahn did have a question about why you used purple or magenta in particular in the global attribute browser, and you had a slide on that came up afterwards. But you could go back and make sure that that we understand why does things show up in that tree in purple?
Why do things show up in that tree in purple? I can see where that might be redundant. The reason here is you can quickly tell whether something is an attributable object if it's bold and magenta, whether it's merely an attribute, or if it is a attribute group. So attribute groups will be magenta. Standard attributes will be non-bold and black, and attributable objects will be bold and magenta. Because there's no limits on what you can name things. You could call this attributes. And without, let's say this is over here, if we didn't have that bolding and magenta coloration, it might be much harder to tell what's what.
Okay, I think that should answer it. Yeah, OpenVSP in a lot of places doesn't control names, and so if you're sadistic, you could name everything Bob. The wing could be named Bob, the attributes could be named Bob, the parameters could be named Bob. It could be that all the way down, and it would just be completely meaningless.
Yeah, you can change multiple data names at once in the attributes editor too, if you want to be sadistic, as was said.
So
I recommend against this, but you can do it.
It wouldn't be a VSP workshop if we don't show people lots of things that you can do but probably shouldn't.
Any other questions, of course, happy to help.
Sounds good. Well, thanks, Tim. Appreciate the talk this morning. The attributes are incredibly useful, and as has been mentioned in the chat and kind of discussed here, that where this can go is still kind of to be determined. I think it's adaptable in so many different ways, and it's going to be really cool to see what people do with this.
Absolutely.
But
It's
thank
been
you.
designed with no guardrails, so go wild, have fun. Thank you
Who
for your
likes
time.
guardrails?
Pleased to present.
Yeah, thanks, Tim. Really appreciate it. Thanks for kicking us off today.
Absolutely. Hope to catch you all later on the stream. Bye for now. Thank you.
All right, and up next, Rob is going to continue on our discussion this morning, leading into sets and variable presets and touching on the new modes. So, Rob, when you are ready, you're welcome to go ahead.
Thanks a lot, Brandon. Thanks very much. I wanted to pull up today's agenda just to sort of talk about a little bit of the story arc behind the day, a little bit of the method to this madness. We kind of have a few things here in the morning, which, as Tim mentioned, are all related to the Navy development that's been going on. We talked about attributes, I'll talk about modes, and then we'll talk about the geometry analysis. We're going to take a little bit of an interlude where we talk about VSPRO in the middle of the day. And then we're going to come back and sort of pick up where we left off with the geometry analysis to do a deep dive into those topics. And then Max will do a demo of using all of these features that from what Tim and I have talked about throughout the day. So we kind of have, one big story arc that is the beginning and the end of the day. And then in the middle, the other big development that's been going on in the background is a lot of VSPRO work that Dave and I have been doing. And so really today is about a lot of things. These are not, well, attributes are released and modes are released, but the rest of this today has not been released yet, but these things will be released very soon. And this is a huge amount of the development that's been going on for the last at least year, and in some cases much more. But so that's kind of the design of what's going on today. And so let's go ahead and move on and get into the talk about sets, variable presets, and modes. Okay. So we'll start by talking about sets. And sets have been in OpenVSP since the first OpenVSP. No, since the first version 3. And what a set is a way of organizing the parts in your model by the purpose, what you're going to do with those parts. And so what this really means is that when you're doing different analyses, when you're doing different things with your model, you don't really need all the components all the time. For example, if you're doing aerodynamic analysis, you only need the OML components, and you don't need, the parts on the inside. Whereas if you're doing a mass properties analysis, you're going to need those parts. And so sets allow you to group the parts of your model, the components, based on what you're going to do with them. So every geom, whether it's a wing or a pod or fuselage, it can be a member of more than one set. You can name the sets, and then you can think of it as sets are the noun, that then the analyses are the verb. We're going to perform an action on a set. So that's one way to think about it. These are everywhere in OpenVSP. Every analysis, every export has them. The API supports them, and they're really used everywhere. Sometimes you might even want to have pseudo duplicate components in different sets. For example, I often have a cruise clean wing in a set, and then if I have high lift components or so a dirty configuration, I'll have those components in a different set. So that's one use. Or I might have a complete wing, and maybe this wing has complicated winglets and complicated planform brakes, and that'll be the real wing. But then I want a very simplified single trapezoidal wing to act as my reference wing, because I'm non-dimensionalizing it by an idealized trapezoidal wing. So then I'll have another wing that's my reference wing, and it'll just be in a different set. So there's lots of ways you can use this. And I will say sets are a power feature, right? A lot of new users don't even know they're there. They don't use it. They don't understand it. And but once you figured it out, once you understand them, you're going to wonder how you ever used VSP without sets. They're just that kind of a feature. As I said, any geom on the general tab, there's this set list, and it's a checkbox. So we've got the names of the sets here, the set chooser, and in this case, the front wing. You can just come through and click the boxes for which sets it's going to be in. So obviously, any geom can be in more than one set. You do your actions on the sets, So sometimes, that's fundamental things are like show only, no show, or select all are things you can do to sets, and in addition to analyses. Down here in the bottom of the Geom browser, we see how to interact with sets with these fundamental actions. If you're using the API, people get confused because what shows up here as set_7, the way things are implemented, the first user set, so set_0 is really numbered number 3 under the hood. And so if you want to access set_7 through the API, then you're going to just use the enum set_first user plus 7 plus that n, and that'll be 3 plus n is 10. And that's how you'll access set_7 through the API. So that's just a little trying to document that here for people. It's a little bit confusing. Okay, if you want to get deeper into the sets, you go to the model window, you open set editor, and that'll pop up this window here. And you can see up at the top, you can change the number of user sets. So it defaults to 20, but you can increase to up to 1,000 sets. You can give them names, you can name them. You can control what geometries are in a set. So this is sort of the inverse of going to a geometry individually and telling what set it's in. Here you're going to a set and telling it all the geometries that are in it. You can, of course, from our previous talk, unsurprisingly, you can assign attributes to sets. So you can come in and write yourself a note about why you created this set and what it's used for. There's also some control here to talk about how copying and pasting set membership works, and do you want to copy that membership when you copy the geom. So lots of things to work with sets on a high level. There's another feature that also is lesser used in OpenVSP called variable presets. And what variable presets is a way of saving multiple states of a model. So you think every model is a collection of params, and all these params have variables, have settings. And what you can do is you can save different sets of params to a model. And there's lots of use cases for this. For example, any geometry that has articulation, you might want to save the variable settings, save the preset with the landing gear up and down, the flaps up and down, the wings folded or deployed, the tilt rotor in different positions, swept forward, swept back wing. All these kinds of things you can capture through variable presets. You might want to have different resolutions in a model. So you might want to have a fine resolution version of the model and a coarse resolution that you use for different analyses. And if you're switching back and forth between this and doing it manually, it's a real pain, but you can use variable presets to make it very quick and easy to change the resolution of the model. If you're doing an optimization study, you might want to store multiple solutions to that optimization study as a variable preset. You can have the baseline case, and then you can have the optimized case. But of course, optimization depends on your objective function. So if you're doing an airplane design, you might say, okay, this is my minimum fuel burn design, whereas you have a different minimum gross weight design and a different minimum total operating cost design. And you can save each of those designs as different cases in the variable presets, and then you can very quickly switch between them in the GUI. One last example is any aircraft that has a variant. And now whether that's variants that we would admit to, like a family of airplanes, like a 737, a Dash 789, you could have different versions of the model that just change the settings and do that. But you could also make that a little bit more abstract. If you had sort of a generic twin engine, single aisle transport, or even wide body transport, a generic twin engine transport model, you could have different variable presets that you could click through and change between different Boeing and Airbus products. Oh, and like with sets, variable presets are also a power feature. A lot of people never use them, don't even know they're there. But once you've started using it, if your models and your processes have this kind of complexity, you'll be really glad that you use it. So like sets, there's a variable preset editor under the model window. You just go up and open up variable presets. And then there's 3 tabs. The first tab is just a way that you can toggle between different settings. So you've got different groups of settings and then different values. So the group of settings might be something like the configuration of the airplane, whereas you might have then a different group of settings for, say, the resolution of the airplane, or another group of settings for this is my optimization solution. So those are different groups of settings, and then each one has different choices within it. And you name the group of settings. You then grab a bunch of parms and then you get different settings. And so once it's all set up, you'll just use this front tab so that you can just switch quickly between different cases. And I'll demo this in a little bit. Under the group tab, well, this is both showing the group and the settings tab, but the group tab is where you name a group, you add a group, you delete groups, you can work with them, and then you can drag and drop what are all the variables that that group controls. So you can drag all the different variables down into that group. And then to control the individual setting choices, you go to the settings tab and you can name those as well. And you can then adjust the values. And so you can come in here, you tweak the values. And then if you want to save the values of a particular setting, you click update and that'll update that one. So whereas apply will take these numbers and apply it to the model. When you click update, it'll take the values in the model and apply it to this setting. I hope it'll make more sense when I demo it. So modes are a brand new thing. It's been out, I guess, for some time this year. And what modes are is sort of a mashup between both sets and variable presets. So sets are a way, as I said, of organizing a model by purpose. We group components, and then we use that set to do an analysis. Variable presets say the state of the model. So it's values for a group of parms. And so what a mode does is a mode is a combination of both sets and variable presets. And I'll have to get into this to show you, but it allows you to put both of these together and then apply a mode before you do an analysis. And again, this is mostly important when you have a model that takes different states, like say a tilt rotor aircraft or something else where you've got different states that you want to be able to switch between, say, cruise and hover, and you want to be able to then do different analyses depending on what mode you're in. So the idea is just like I said, you take sets and you take variable presets and we combine them together in order to make modes. And then when you're doing some analysis like CompTIOM, instead of choosing the set, you can now say, oh, I want to choose a mode, and then I can pick between which mode. And what VSP will do is when you run the analysis, it will first apply the variable presets to make sure that you have those settings applied, and then it will choose the set of components, and then it will run the analysis. Just like set and variable preset, you access this through the model menu. You open up the mode editor. You have all the modes up at the top where you can name them, create, and all of that. You say which sets are in it. And so every mode can have both a normal set and a degen set. I'll talk a little bit more about that when we talk about VSPRO just after the break. And then you choose which different variable presets are going to be applied when you run that mode. So you can choose one variable preset for each group, as much as that if you want. And then, of course, following Tim's talk, unsurprisingly, you can then apply attributes to modes. So if you want to have notes about why you created the mode and what you're doing with it, there you go. You can do attributes. All of this is available through the API, so you can manipulate, and I didn't show the API for sets and variable presets, but those have API calls, as does modes. Sometimes there might be some confusion if you're looking for how do you tweak things a little bit deeper, but as it turns out, a mode is in fact a parm container. And so, and the normal set which you would choose is a parm. And so to access and change things like which set is in a mode, you use the parm container API in order to change that mode. And so let me just go and I'll do a quick demo here just to sort of show a little bit more about how this works. And if anybody has questions, go ahead and type them in the chat, and I'll try and look at them as I go. So here is a generic tilt rotor model, and we have both sets. So we'll come into the set editor first, and we can see this model has a whole lot of sets, and I'll show you why later in the day. But for example, we have a set of just the lifting surfaces. So I can come in here, for example, I can choose the lifting surfaces and I can say show only, and that gives me all of the things where a kata condition might be applied. We can come in and talk about and show a set of just the tilting components. And so let me show only, not show. There we go. So these are just the parts of the model that tilt and not the parts that don't tilt. The fixed components are all the parts that don't tilt. So that's, and don't move in any way, right? Because this wing also pivots. Those are all the fixed components. So we can use sets in that way. And again, we can control the membership and interact with them like that. Let me select all and show everything. Then we can come in here and we can go to variable presets. And so in this model, we're only using one group, which is the configuration. So this model didn't have, different optimization solutions. You could conceivably morph this model into, an Augusta Westland a 609 or a Bell 280 or a V22, so that it could be a sort of a generic tilt rotor model. I haven't done that. The only one I have is configuration. So we can switch to either the stowed, hover, or cruise variable preset. So here we are in cruise. So let's say if we want to go look at hover, we can apply that. Or if we want to go to stowed, we can do that. And you can see that it's just changing the variable settings. These are all controlled with hinges. So we have a hinge at the root here and a hinge at the tilt axis. And then we have the propeller folding like Brandon talked about yesterday. And so all we're doing here is changing a bunch of parameters to quickly change this model between these different states. So that's how variable presets work. Again, we have the groups of it. We only have one group on this model configuration, and these are the parameters that we're changing, the different propeller fold angles, and then the two joint axes positions of the hinge. And then the values of those settings are back here. You can see that for hover, we have different values, and these should be updating. I'm not sure why we're not updating in this list. I'll have to go look at that. Okay, so that's how variable presets works. And then really the new part that we're talking about today, the part that's novel and different, is the modes. And here I have a lot of modes in this model, and you'll see why a little bit later today. But what we have then is a combination. And so some of these have kind of crazy names, but for example, my cruise arrow mode, if I then apply and show only, what that's going to do, and that should certainly be showing the wing. I'm sorry, this is another bug that I've run into that I think I just caused recently. So the wing is actually shown, but it's unfortunately in the wrong state. So let's just change that back to normal. Let's select all and make them normal. I've got something wrong with how I'm previewing degen geoms. So when that switched to showing the degen set of cruise wings, it didn't visualize them right. So I need to chase that down. Okay, so that would be the cruise arrow in this model. We've got hover arrow, and then we've got, different things. And I'm really kind of slicing this onion thin. Again, you'll see why later, for things like, here's just the stowed props and other things that I'll show. But modes allow us to control, both the state of the model and the components that we're interested in. And that's really the bottom line. So I'm finished a little bit faster than I thought. I'm happy to take any questions here in the background if anybody has any questions in the chat.
For the demo, I haven't seen any specific requests, but we'll let things catch up online here just a little bit. All right, well, we got about 10 minutes before our next scheduled presentation. Rob, if there's anything that, let's see, a question just came up, says, can you also change the size of propellers? Yes,
Yeah,
you certainly
so
can.
so certainly let me show this prop and let me change back to a cruise mode, or variable presets. We'll just come back in here and apply our cruise state of the model. And let's just show all. So here's the complete model. And certainly, if you want to change the propeller, you can come in and on the design tab, here's the diameter of the propeller. So in this case, this model looks to be in inches. So let's just make it 90% the size that it is by multiplying it by 0.9. And so we can change the size of the propeller. And if we wanted to make that a part of the variable presets, we could, or we could certainly come in and we could say, just as a demo, we could have, okay, we had a configuration variable preset. Let's go with something like, rotor size. So we'll add that group. Now we have a rotor size group and it doesn't have any variables in it yet. We're going to want to put diameter in that as a setting or as a variable to be set. We'll have small as a small rotor and we'll add that, and that's the current setting. And we'll add another one and we'll say normal. We can add that, and then we'll come in here and we need to apply a value. So we're going to multiply that by, divide it by 0.9. And so then we'll update that setting and then we'll have a large. And so we'll make it again 10% bigger by dividing by 0.9. And we will add large as that value. So now we have small, normal, and large. And so now we can come back and say, okay, rotor size normal, we want to apply that. Rotor size small, we can apply that. Configuration stowed, we can apply that. So, any parm we can put in to a variable preset, and then we can use that, of course, in a mode or use it in any of these ways. So yeah, the analyses do have access to modes. So for example, any analysis that you do, it should come in and you should be able to come in, say to comp geom, and you can either choose the sets that you want to apply to, or you can choose the mode. So for example, in this case, if I want to do comp geom on my, my cruise air, let's not do that one. Let's do stowed tilting. Well, we can choose whichever one makes sense. And I'm just thinking about these different ones. They're a little bit complicated. Again, I'll show you later in the day. But if we want to do that on that comp geom, then we can come and just run comp geom on that mode. And so it will apply those variable presets and select that set and then run whichever analysis. And that's going to be true for all of the different analyses. If you come in and you want to do any of these analyses, they should all have if you want to do projected area, you can come in and you can choose the mode for the target geometry. If there's something where you have to choose two different sets, like in this case, you choose a target set and a boundary set, then you don't get to choose two different modes, right? Because if you did, you can imagine if one of these was in hover and one of these was in cruise, that would be completely inconsistent. So anytime you have to choose two groups of geometry, you don't get to choose mode twice. You only get to choose mode once, but then you can still choose the set for the secondary geometry in something like projected area analysis.
It's up about 5 minutes before the next scheduled presentation. If there are any other requests for a short demo, you're welcome to go ahead and post that in the chat, and maybe we can do a quick little demonstration of any specific features. If not, then we can queue up the next presentation, and for the folks that are tuning in online and trying to follow along the schedule, we're avoiding starting anything particularly early. So we'll get things going about noon Eastern here. All right, well, it's noon Eastern.
All
We're
right,
gonna
Brandon, I'll go ahead
and
and
there you
get back
go.
on track. So the next talk on what I'm calling this geometry analysis overview is about a new, not just one new feature, but it's really about a handful of features, really 3 core features that work together to be really powerful. And I'm really excited about this capability for VSP, but I'll be honest, it's a lot of moving parts. In order to make use of this, you have to set a lot of things up. You have to set up an analysis. You have to set up some auxiliary geometries, which you guys don't know what they are yet, and you have to set up some new geometry types. And so there's a lot of things that have to be in place to make this work. And it's probably not very discoverable, if not very intuitive, if you haven't seen this kind of a talk. So hopefully today in the morning sessions and then in my later in the day sessions, I'll be able to explain how this all fits together. And really the purpose of this talk right now is to give you guys the big picture view. Let's give some context about how all these things work and why they're the way they are. And then we'll come back later in the day and we'll do a deeper dive into the nitty-gritty of each of the different steps. So hopefully that context makes sense. And as I said, I'm really excited about what this can do, but there's a lot going on. So what we're aiming for is an ability to support what I'll just generically call geometry checks. And there's a lot of geometry checks in the aircraft design process that are familiar to an aircraft configurator. And all of these checks, in the old days were performed at a drafting board by the configurator, by the draftsperson. And today they're going to be checked by your CAD person, and they're checked in CAD. And checking these is a very manual process. You've got to go and, it's something that's typically not integrated, for example, into something like an MDO or an automated design process. These are a very manual thing. And they usually result in a qualitative result. Either you pass or you fail, and which a pass-fail isn't really suitable for use in an optimization process. And this manual process is actually, these tests are a lot harder than you think they are. And I'll talk about why, but basically the human is actually doing more in these tests than you probably think they are. So what are some examples of this? For example, here's one where you might want to check to make sure that the spinning rotors on a tilt rotor don't intersect with the fuselage. And so do those spinning rotors hit the rest of the aircraft? You also might want to check, do the spinning rotors hit each other? That would also be bad. And so in this case, you'll see I have this little red line showing the minimum distance between those. And in fact, there's going to be a tiny little red line. You can't see it from this angle right here. There's a tiny red line, which is the minimum distance between that rotor and the side of the fuselage. Other geometry checks, you might want to check that does the aircraft in the folded configuration, are there any interferences? Do these propellers hit the vertical tail? Does the nacelle hit the upsweep on the aft fuselage? Does everything clear, or is there any collision back there? Or just looking at the folded propellers themselves, do any of the blades, when folded, intersect with each other? Do they hit each other? And you can see that little red line shows the minimum distance between any of these blades. You might want to check that, do all the things inside the aircraft, all of the things that you've packaged, do any of them overlap with each other? So, is there any overlap between the flight crew and each other, or between the flight crew in this cargo bay? Are there any interference between those? And in this case, there's a little red line showing that the nearest distance between any of these components is between the elbows of the flight crew. Or you might want to check that, do any of the things that belong on the inside of the aircraft, do any of these things interfere with the fuselage? Do any of them protrude outside? Because you don't want the pilot's head sticking out the windshield. And you'll see here's a little red line showing the minimum distance between this cargo bay and the side of the fuselage. You also might want to check, earlier we were checking the propeller arc swing in the cruise configuration. You might also want to check it in the hover configuration. Does the propeller hit anything in hover? On a transport aircraft or a fixed wing aircraft, you might want to check, what is the tail strike angle? And so, when pivoting about however the landing gear pivots during takeoff, what's the first part of the aircraft to hit the ground? And this is one of the cases where I say these checks are deceptively complex. See, when a CAD person is going to sit down and find this angle, they're going to visually look at the model and they'll immediately know that the first strike is somewhere here on the fuselage and somewhere to the gear, and they'll construct a tangent line between the fuselage and the gear. What they did implicitly, though, is they immediately decided that the first strike is not on the horizontal tail or the vertical tail or the engine or the wing or anywhere else on the aircraft. And that checking of multiple components is actually the hard part. And again, it's done implicitly without even thinking about it by the human doing this check. But when you want to go and automate this kind of check, to my knowledge, CAD programs, while they have the ability to construct a tangent line between one component and another that are specified by the user, they don't have the ability to find that line that's the first contact between many possible components. And where that component, which one is the sort of active constraining component, can change throughout the design process. So you also might want to check, the roll angle, rolling about the landing gear. What's the first contact point? Does it hit the engine or does it hit the wing? You might want to check the relationship between the center of gravity and the axis that you roll about. So here I've shown the tip back angle for the most forward, most aft, and the nominal CG location. We also have the tip over angle. So this is between the line between the main gear and the nose gear. And again, we're calculating the tip over angle between the most forward, most aft, and nominal section. You might want to check the ground maneuverability. So what is the turning radius of the aircraft? What's the ground track for the nose gear, the ground track for the main gear? And also then what's the furthest point and what radius does that arc does that sweep? And this tells you, how big of a hangar you need in order to do a 360 with the airplane. And here's another one where you might want to check the visibility. So from a pilot located at this position with some really terrible windows drawn here as subsurfaces, we can actually now go out and calculate what is the field of view in the angle. This is actually projected onto a sphere. What is the field of view that the pilot can see from that position? So setting this up, in the past, most analyses in VSP, things like CompGeom, they have very little configuration. There's only, one or two little things that need to be set up, and they're really easy to do. And usually there's only sort of one setup that you want to do per model. You want to run CompGeom, you're going to do it. If you want to find the wetted area of the aircraft, you're going to do that on the same set every time. And so not saving that configuration or not having a more complex way to deal with that is not really a big deal. Geometry checks, on the other hand, they kind of force a different paradigm. I expect that you're going to need a lot of geometry checks in a model. Just like we said on that transport airplane, you're going to have 5 or 6 or more geometry checks that you want to perform. On that tilt rotor, you're going to have lots of geometry checks that you want to perform. And so they also have a lot of subtle variations, little things, tweaks that you'll want to make, and we'll talk more about these, but adjustments that you want to make to it. And then you want to go back and revisit these frequently. You want to go back and rerun that tip back angle or that tail strike angle. You're going to want to run that over and over again. And so if there's a lot of fiddly settings and a lot of tweaking, you don't want to have to do that over and over. And so you could automate this just by scripting everything through the API, but there's a lot of people who don't use the API. And so what we've done, first thing that I'll talk about, is we actually now have a manager in order to work with these geometry analyses. And so basically this is a GUI where we set up different run cases. And so this geometry analysis GUI, we have the list of different analyses and then all of their settings. It allows you to set up and manage a whole collection of these analyses. And each one has a primary and a secondary geometry, where that can either be defined by a set, a mode, or a geom. And then all of the different analysis options, all the different settings to make them work, and anything else to sort of work with that is in this GUI. Also, it makes it easy to visualize the results and to dig deeper. Lots of times, these analyses will calculate a whole bunch of different things. A whole bunch of different numbers will come out of it. And so, rather than just show you a single scalar, you can dive deeper into these analyses. So that's what I'm talking about, the geometry analysis manager, and we'll dive deeper into that in a minute, but that's sort of the setup there. You may have noticed that a bunch of these analyses that I just talked about, and if you're a configurator, a lot of these things revolve around the landing gear of the aircraft. And so, in the past, people have built landing gear models of their own airplane, but usually they do it, with just a bunch of stacks or fuselage components. And rather than doing that, to make this really work, we need a dedicated landing gear component. And what this does is because it's a dedicated landing gear component, that means that my analyses that I'm building for you, these analyses can know that, hey, this thing is a landing gear, and so it should behave like a landing gear. It should rotate about the gear. The gear can be castered or not. It knows about the contact points. It even will know things like a tire can deflect, and it's either going to be sitting at the static loaded radius or the first contact point, or even a flat tire where it's riding on the rims of the wheel. These are all things that it can know about the fact that it's a landing gear. It can know that the strut is compressed or the strut is extended. And then it needs to know about the center of gravity envelope. So all these things need to be built into the landing gear. And because of that, I've built a new landing gear component for VSP. Some of these checks that we're going to do are done on a part of the geometry that's not really an explicit part of the geometry. And so, for example, the arc that a propeller swings through, including some flapping angle fore and aft, that propeller arc is not an explicit model of the geometry, right? That's not something that you model, you know, I mean, you could if you had to, but it's not something that you should have to model in your aircraft. But instead, it's something that, given the definition of the propeller, I have enough information to just be able to quickly generate that propeller arc swing for you. So without you specifying much more information, you only have to specify the forward and aft flapping angle. I can take what you told me in the propeller, and I can build that propeller arc swing or that burst cone. If you want to look at, okay, if I throw a prop and I need to look at a 15-degree angle in front of and behind that rotor, that burst cone, again, you don't have to build that geometry yourself. I can build that using what you already told me about the prop. And this is true across the board. Things like the landing gear, it's one thing to define the landing gear state, but lots of these checks need to be performed in an off-nominal landing gear state. So either a flat tire, a compressed oleo, an extended oleo, you know, tire on one side flat, but the other side is extended, sort of worst case scenarios. And so all these off-nominal landing gear are also things that we can work with. And so this general concept, which is these geometries that we're going to define based on another geometry, we're going to call these the auxiliary geometries. So there's three concepts I've hit. We've got the geometry analysis, we've got the new landing gear component, and then we have the auxiliary geometry. And so that's sort of that background. And I'm going to quickly just go in and do a little bit of a demo to again, just give a teaser. But again, this afternoon, I've got two really deep dives into this topic that should go into more. Okay, so, and I see a bunch of chatter in the chat. I'm thrilled that people have the same enthusiasm for this that I do, and I think that you guys are nailing the use cases and how they relate to modes and these other features and how all this stuff comes together. So let me just open up, for example, that tilt rotor model that I kept talking about, why some of these things would make sense later today. So let me shade it and come in here. And just as an example, again, this is all set up for us, but if I come in now, oops, you know what? I ran the wrong version of VSP. Let me look, I have to run the version that actually has all these features in it. So, and hopefully I didn't hit save earlier and lose all those settings. Let's just make sure that it's still all in here. Okay, let me come in here into the geometry analysis. And you can see I have a whole bunch of these geometry analyses. And so, you know, the cruise prop is a geometry analysis. And let me just show only that state. And so what you can see is we've now applied that mode and shown the auxiliary geometry. And so what we have here is the cruise prop interference is, does the auxiliary geometry of the propeller clearance geometry, right here called propeller clearance, does it interfere with any of these components that it shouldn't interfere with? So does it hit the wing and does it hit the body? And let me just come in here over to this one and I'll say, let's evaluate that analysis. And so we've just done that calculation, and you can see there's the little red line that shows there's the closest approach. And I'll show you what it does when it violates that later today. But, we can just go through and I can show, here's the propeller clearance. Do they hit each other? If I want to check the stowed configuration, here's the components that are involved in checking the stowed state. And so let's evaluate that analysis. And you can come and you can see that right now the minimum distance is between the nacelle and the little ducktail back here on the fuselage. And, we can go through and show all of these if we needed to. We can evaluate all of them. Some of them aren't evaluated right now. We'll just show a couple more. So here's the propeller, the mutual interference between the props to make sure that your fold solution is good. Here's the packaging. Do the things that are supposed to be inside the airplane, are they inside the airplane or do they protrude outside? And here, the minimum distance between these things and the outside of the airplane is this little red line here. Here's the mutual packaging. Do the things that are supposed to be inside, do they overlap with each other? So here we can show, the minimum distance is the elbows of the flight crew. And, here's my, does the propeller in hover, does it interfere and hit anything? So there's the analyses that are set up in this model. Again, we'll do a deeper dive later today. Let me open up that transport model just so that you can see what the same kinds of things that it does. So here's that model with the landing gear, and you can see we've got our flight crew and some really terrible windows. And we can come in and we have all of these different analyses. I'm going to evaluate them all just so that it'll go through and run all the calculations. That way I can quickly click between them. But let's show only the things that are involved in tail strike. And so you can see the tail strike, we're pivoting about the main gear. And then there's that angle of nearest approach. And if I want, I can even apply that rotation to the landing gear, and I can show that this landing gear is rotating about the pivot of the bogey. And that's then what the ground plane looks like when it hits that tail strike. And that's an off nominal landing gear that we're looking at that with. We can show, here's our tip back angle, which I'm still showing in the off nominal. So let me, here's our 2-point ground mains. Let me come in and change that bogey angle back to 0. And so here's our tip back angle calculation with a vertical line shown in the most forward, most aft. Tip back angle calculations. I see someone just asked if that they don't see this in their version, and you're correct. This is not yet released. This is a preview of something that will hopefully be released. I'll call it within the next month or so. This is almost ready for release, but it's not out there yet. Okay, we can look at our roll strike angle. So here we are, we're pivoting about the right gear in this case, and we're finding what's the angle that we first hit. We can come in and look at our tip over angle. So there we're rotating about the right gear and the nose gear. And again, with the most forward, most aft, and nominal CG locations to find those rollover angles, tip over angles, sorry. I actually calculate, this one's not very graphical, but I calculate the distribution of weight on the main gear. So it reports out what's the fraction of weight on the nose gear. So in the nominal CG location for this configuration, 8.5% of the weight is on the nose gear. I calculate the turn radii and, what's the ground maneuverability. We have, the ground and ceiling clearance envelope. So in this case, it's the distance between the ground, the lowest part of the aircraft, but also the distance between the ground and the highest part of the aircraft. So you can, how tall does the hangar need to be for you to fit in that hangar? Here's a neat one. If you're landing a narrow body transport on an aircraft carrier and you need to know, does this aircraft, hit any of the equipment on the deck of the aircraft carrier, you can put in a profile that represents all of those obstacles and the user supplied profile. And then we'll check, do you hit any of those things? And finally, the last one I'll show here is a pilot visibility check. So here what I've done is we've actually come in and we have the pilot and we have their nominal eye point, the design eye point, which is just the average between your two pupils. And we've drawn some really ugly windows on this aircraft as subsurfaces, but then we found what is the field of view of the pilot through those two windows. So we can see this is what is visible for the pilot from those windows, and we can use those to check all kinds of visibility checks. So yeah, so again, there's going to be 2 more deep dives. I'll just go a little bit deeper just to say that all of these things, let's go to say the carrier envelope. Let's show that one. So this is based on, right, this carrier envelope is a special kind of off-nominal state of the landing gear, and that's the CCE ground. And so there's other parameters involved in it. For example, there's a parameter to control how far off of axis the main gear is placed. And so this model is, I believe, in feet. And so there's a requirement that I've seen that the Navy says you have to be able to, the main gear can be off axis by as much as 24 inches. And so if we put in 2 feet, that places the main gear off axis by that. But then you might also have a problem where one of the landing gear, the suspension, instead of nominal, is compressed. And so there we've compressed the left gear. And, the other gear, the opposite gear, is extended. And on the compressed side, the tire might be flat. And so you can see that if with these gear extensions and a flat tire, we're actually already hitting the nacelle. But what you can do is you can set up this off-nominal gear location, and then we can come back in and we can run that analysis. And what it'll do is it'll come back and it'll tell us, that we interfere. And you see this red volume down here. It's actually calculated how much of the model violates that state. And so you can see that this isn't just about the nominal landing gear, but about all of these off-nominal conditions and being able to quickly control them and check all of these different checks. So I'm going to stop there. I'll go back to the chat if anybody has quick questions. Like I said, later in the day, this talk that I give after the second break is going to be a deep dive just into the landing gear and all the landing gear related analyses and auxiliary geoms. And then after that, I'll do a deep dive into the geometry analysis manager, and then also talk about all of the other checks, which is going to be a lot of. So this one will mostly be the transport airplane cases that I showed, and this one will mostly be the tilt rotor aircraft cases that I showed. So we'll do a deep dive into both of these subjects where we'll cover a lot more detail. And then the last talk of the day, Max is going to do an actual talk about a demonstration case where he's been using attributes, modes, and geometry analysis to do an actual design study and optimization study as a demonstration of all these new features. So we'll get to see what Max has to say about that. So that's kind of the story arc for the rest of the day on this topic. And not to sell the VSPRO stuff short, I'm actually incredibly excited about this stuff too. Also not released yet, but hopefully very, very soon, this VSPRO stuff. So today is really a big preview of things that are going to come. So Zach, you asked what comp geom and what section is used for the rotor blade volume. I'm not sure how to understand that question. I assume that we were at least talking about the tilt rotor model. And here, are you talking about the, if you could clarify your question, I'll try and answer it. Okay, great. Glad I answered that. Also, Keith, I saw your question about the windows. So, and so we'll talk about that more when I talk about the pilot visibility geometry check. Certainly, in terms of, making something transparent, making this fuselage, that's just choosing this material. So here I've chosen it to be, semi-transparent. So you can choose it to be glass. You can choose the whole thing to be ruby is one of my favorites. It's a nice shining red. You can also make custom colors. So you can come in here and customize that material. If you like the ruby, but you want it to be transparent, you can dial in. You can dial in transparency on any of these colors, and you can save that and give it a name. Now, obviously, that's applying to the whole thing. In terms of windows for doing that analysis, what we're going to do is we're going to apply subsurfaces. So we can come in here and basically we draw a rectangle as a subsurface. You can see here it's in red. Turns out turning this to ruby when I was going to demonstrate something in red was a bad choice. So let's go back to glass light. So our subsurface, this rectangle, what we're doing is we can move it around. So this rectangle is drawn in those UV coordinates that I was talking about during the geometry talk yesterday. And so we can basically draw this as a rectangle that we then, it's a rectangle in UV coordinates. But so we might be able to use that to then represent a window. And, again, this is a pretty ugly window. Another preview that we'll see here later today is we now have the ability to we have much more flexibility in how we design subsurfaces. So I won't spoil my own thunder there, but there's going to be a lot more. But yeah, so what you can do is you can draw a window like that using a subsurface, and again, it's not showing this is transparent and this is opaque, but it does show that window. And then now when we do the analysis for the visibility, it can actually cut out that window and project that forward. All right. Well, I'm not seeing any more questions in the chat, so I'll go ahead and wrap it up, and we will reconvene here in half an hour to talk about updates on the VSPRO geometry handling. And I look forward to seeing you there, and those of you on the East Coast, enjoy your lunch.
Thanks a lot, Rob. We'll see you here in 30 minutes. All right, everybody. It's about 1 o'clock Eastern, 10 a.m. Pacific time. We're going to get started with the next OpenVSP Workshop presentation here with VSPRO geometry updates. And without further ado, Rob, you're welcome to go ahead and get started.
Thanks a lot, Brandon. I appreciate it. I hope everybody had a nice little break. So there have been a lot of changes going on behind the scenes with VSPRO. You may have noticed that we haven't updated the solver itself in the publicly released version for a long time. And that's because there's been so much going on between Dave and I back and forth that we've really built up, honestly, 3 years worth of work that is all just about ready finally. And so on the OpenVSP side, I'm going to talk about those changes. Then Dave will talk about all of the VSPRO, what's going on with it, and then I'll come back and I'll do a bit of a demo where we actually run the code after Dave's talks. Okay. So if you actually go and dig into the source code of a legacy potential flow codes, take PMark for example, you're going to find that a huge amount of the code, a large fraction of the code, is actually there for geometry generation. And this goes into what I talked about yesterday, where legacy codes had their own geometry tool built in. And it takes a lot. In fact, if you look at PMark, there's more code for geometry generation than there is for the actual flow solver. So VorView was a geometry processor to take RAM files and turn them into Vorlax analysis files. And it had been integrated into OpenVSP 2. And Vorlax is a Lockheed/NASA Vortex Lattice code from 1977. And Vorlax is an interesting case because we used this with VSP before it was open. And the writing of Vorlax, 1977, predates the modern application of copyright to software. So Vorlax, by definition, was in the public domain. Unfortunately, it had been passed around from company to company to government and back to companies, and it had been passed around for 40 years. And so when we were releasing OpenVSP as open source, the NASA attorneys didn't have an audit trail that they felt that they could really look at it and say, yes, we're clean. We have rights to release everything here. And we were trying to figure out what to do about this because we really wanted a similar analysis capability. And I had a student who was working on something called dgen geom that you're familiar with, and we'll talk more about that later. And Dave saw the dgen geom work and basically said, look, it'd be easier for us to just write a new Vortex Lattice solver than it would be to deal with the lawyers and get this cleared. And so that's what happened. So if you look back at old school VorView and Vorlax, we could take a RAM model like the one on the left, output a wireframe like this Hermite file here in the middle, and then process that using VorView into this flat plate over here on the right. And this is the kind of smashing and combining and slicing that it would do in order to create the geometry. And it worked fairly well in cases like this, or at least not overly objectionable. But when you would apply it to more complex cases, it would sometimes become unruly, as it would do this smashing process. If you wanted to keep the camber surface, that would keep some tangent angles like this. But you would often end up with nasty gaps between here, the wing and the side of the fuselage. And these nasty gaps would wreak havoc on the solution. Likewise, here, if we had a T-tail, you've got this huge gap down the body at the center, and this really just wasn't very satisfying, wasn't very good. So you would usually end up doing things like dropping the engines and dropping the empennage and just running a wing body, which would get the analysis to work okay, but it wasn't necessarily really what you wanted. So like I said, dgen geom was something that my student Joel Belbin did back in 2013, is when he finished his, presented at the workshop for the first time. And what it does is we can take each individual component and we can degenerate it. And we can degenerate to a surface, down to plates, down to an equivalent line, and even down to a point mass. And the idea was, instead of, most output files from a code contain exactly the information that one downstream analysis is going to need. And instead, with dgengeom, we took a kitchen sink approach, which is let's put everything we can think of into this file, not knowing what it's going to be used for later. And that's had some really interesting results over time. So VSPRO was developed to use dgengeom originally to provide a vortex lattice type calculation for OpenVSP. The first dgengeom release that was public was with the first version of OpenVSP 3.0, which was in January 2015, and 3.1 included the first release of VSPRO, which was really exciting. And the first time we ever talked about it at a workshop as a preview was in 2014. There's been lots of evolution, going from just a thin surface mode to a thick surface mode that we called panel mode. That happened with the first release of that in version 3.9 in August of 2016, along with the first workshop there that we talked about that. So then we had either a thick mode or a thin mode. So let's talk a little bit about the geometry in OpenVSP. Here's a very simple airplane, a pod wing with a vertical tail. And here we're just looking at the wireframe in a hidden view. And so you'll notice there's no intersection that's been performed at these joints. So we have a thick wing and a thick body, and there's been no intersection been done. We're just, the wing is passing through the fuselage. And that's just the normal OpenVSP wireframe. So when we would do dgen, we would smash all these down to thin surfaces, and you see that the wing becomes this curved mean camber surface, and the fuselage becomes this cruciform, and the tail is a flat plate that then is coincident and overlaps with that vertical part of the cruciform on the body. And so in a dgen geom, which is what VSPRO was originally written to work with, no intersection calculations are performed between these. There's no trimming, there's no union. These are all just separate panels that happen to be, flying in close formation with one another, with no actual connection between them. When we went to the panel method, when we added that thick panel method capability, we used the output from CompGeom. And so here I've run CompGeom on this geometry, and you can see the first thing CompGeom does is it drops in the diagonals to turn all of those rectangles on the surface into triangles. And then we perform the Boolean operations, that Boolean union between these. And you can see we end up with this trimmed surface. So now we know the curves, we know the intersection between the wing and the body, and anything of the wing that was on the inside gets thrown away. And so we have an accurate representation of the OML. But the problem with this is we end up with some really low quality triangles. We end up with these really thin slivers along this intersection, along this joint, where all of these things come together. But this is what we would feed to VSPRO to do its analysis. And then what VSPRO in panel code mode, what you guys are familiar with today, what it would do is it would try and go through and clean that geometry up. So it would do the best job it could with the limited information that was in the file to remove those diagonals and get some rectangles back. And then it would go along these joints and it would try and remove some of these slivers and try and improve this geometry inside. And you can see it's cleaned up, but it's not perfect. There's still some of these nasty thin sliver triangles. We have some places like here around the nose where we didn't remove the diagonal, and things where it just got a little bit confused or it wasn't able to do a perfect job. But it's not bad. It did, what it could. And then it would analyze this for the thick surface. So one of the things I've been working on lately is what I'm calling the Ngon mesh. So before, that mesh was made entirely of either quadrilaterals or triangles. And what I've done now is instead of having VSPRO perform that cleanup after CompGeom, I do that cleanup in OpenVSP. And I can do a better job simply because I have more information. I have more information about where those panels came from and about what their origin was. And so what I can do is after we do that CompGeom and we have all the triangles, I can go back and I can remove diagonals to reconstruct triangles both into quads, but actually here at the intersection, I'm actually reconstructing it into a polygon of an arbitrary number of sides. And so just quickly looking at it, this polygon right here is going to have at least 1, 2, 3, 4, 5, 6, 7. It's going to have at least 7 edges to that polygon. And the nice thing is that this polygon shape, right, is able to really clean up that geometry. It's really able to get rid of all those thin slivers and distill it down to a much, much cleaner geometry and recover something that's really very nice. And the good news is that the way VSPRO has been written is VSPRO, all of the fundamental potential flow elements that it works with are actually edge-based. They're not panel-based, it's edge-based. And so each panel is a ring of edges. And so VSPRO is able to work with a multi-sided polygon just as it works with a triangle or a quad. And it actually already used this, for example, in things like the agglomeration that it does, where it groups a bunch of panels together. It would then work with the polygon that was the outer side of that grouped panel. So this is one thing that's been added to the geometry, is we're moving to this end-on mesh. And another thing that I worked on was the ability to do an intersection between a mixed mesh, so that here you see the wing and the vertical tail are being represented as thin surfaces, degenerate surfaces like we did before, but they're being intersected with a thick surface, in this case, the pod fuselage. And so now the wing, this degenerate thin wing, intersects, but whatever was on the inside is now trimmed and thrown away. And so now we have this combined mixed thick thin mesh of n-gons, of arbitrarily number-edged, number-sided polygons. As an option, we also now have the ability that if you choose everything to be thin, so thin fuselage and thin wings, we can still do the intersection. And so here it looks a bit odd perhaps, but we've intersected the wing with the body. And so you can see they're actually now connected. And it's a little tough to tell, but actually the vertical tail has been intersected with the fuselage. And so there's no longer any overlapping triangles or any overlapping panels back here. The fuselage is actually cut out and connected to this vertical tail. So there's no longer any coincident overlap. Everything's trimmed, even though it's all thin. And this is just the geometry side. But one of the things that Dave's been working on is then being able to handle this on the analysis side, so that now the solver, VSPRO, can work with these, and I'm going to back up one, can work with a mixed thick and thin geometry. It can work with this and perform a solution on this. And so the flexibility this gives us is in OpenVSP, instead of choosing that everything has to be thin or everything has to be thick, which was VLM or panel before, that now loses meaning. And we now can choose on a component by component basis, oh, I want these components to be represented thin, and I want these other components to be represented thick. And then I can combine them with this n-gon mixed mesh, feed that to VSPRO, and VSPRO can perform a solution on that mixed geometry. So there's some other little tweaks that we needed in this. So there's a feature that I'll show you here in a bit called cull orphans. And basically, here we have this is the thick representation, but this is a representation of a strut braced wing. And here you can see that we have the strut and this little jury, this little leg right here that comes together. And in this case, the strut was built a little bit carelessly in that the strut actually protrudes out the top surface of the wing. Now, normally, if this was panel code, I'd say, shrink that back down, get your intersections fully buried, and do the intersection, and the panel code will take care of it. But the problem with that is, well, what if you wanted to use thin surface representations for these struts and jury and the wing? If you want these to be thin, then it's basically impossible to get that intersection right? The advice of working with a thick surface, where I say just bury the intersection in the other surface and let it be deleted, doesn't work. And so if you just did a thin surface intersection without anything special, you end up with these little stubs. You'll see there's these little stubs that stick out of the top where the strut comes up, and then the jury protrudes out the top of the wing here, and it protrudes below the strut down here. And so these little stubs are what I'm now calling orphans. And orphan panels are thin surface panels that are topologically connected to one another, but not topologically connected to the rest of their component. So you can't, if you were to walk edges without crossing this green wing, you can't walk from this little area up here, the orphan, you can't walk the mesh and end up down here on the main part of the jury. And so those are orphan struts. And so the cull orphans option that I'll show you, it will then delete those. It'll delete all the orphans, and it uses one more filter. It does it based on the area fraction. So you put in a number, say 5% or 10%, and it'll then delete any orphans that are any orphan panels that are together less than 10% of the area of that component. So that way, if you have something like a T-tail where you have, two big pieces that would otherwise be considered orphans, well, they're both 50% of the area. So you can set that fraction so that you don't cull the T-tail. But if you do have little stubs like this that are poking through your intersection, you can trim those little stubs so that you can clean it up. And even though on the right, even though this is a thin geometry, you'll see that we have proper intersections with no protrusions and everything's trimmed to what you want it to be. So this is in what'll be released soon, and I'll demo this in a minute. I'm also going to tell you some things that are going to be released even later. But another thing that I've developed is the ability to write a multi-resolution NGON file. So what I've done here is on the left is something like that NGON I showed you earlier, where I've done that intersection. But what I've actually done in this case is each of these meshes represents a doubling of the mesh. And so we have 1, 2, 3 doublings. So there's 3 doublings over on the right. And what I actually do is I generate this mesh on the right first. I generate the fine mesh, and then I do the NGON processing. I do comp geom, and then I do the cleanup so that I have a nice NGON mesh. And then again, since I have lots of information about where these elements, these panels all came from, I then go through and I de-res it. I remove every other grid point, essentially. And I de-res it from this finest mesh to the next one. And then I de-res it again to the next one. And then I de-res it again to get this coarse mesh. And what this allows me to do is I now have a family of meshes of the same geometry, but at different resolutions. And moreover, every node in this mesh, in the coarsest mesh, is exactly known as a node that was also in the finest mesh. And so the coarsest mesh, the node points that you see there, are a strict subset of the next finer mesh. And that mesh's nodes are a strict subset of the next mesh, and those are a strict subset of the finest mesh. And so I can actually write this multi-resolution information out to a single file where that file contains all 4 versions of this model, but all based on a single set of points, just using different connectivity information. And I can also specify in that file that lineage where, the coarse mesh has a certain set of panels, and then those panels are divided in 4 to become the next finer mesh, and those panels are divided in 4 to become the next finer mesh, etc. And we aren't using this yet. This is just a geometry capability that exists, but the idea is that we hope to be able to use this to be able to study the effects of mesh resolution in a VSPRO solution, looking at estimating the error due to the mesh, and potentially someday we may be able to do something with that information. And it should be really cool. Now, there is a difference here. We have even though these 2 meshes look mostly the same, I want you to look here at the leading edge of the wing where it meets the fuselage. And it's interesting because on the left, what I have is that coarsened mesh, where I started with a very fine mesh and I coarsened it down. Whereas on the right is where I generated something at the same resolution and I just directly jumped straight to that mesh. And you'll notice on the left that this curve is sort of concave between the fuselage and the wing, whereas on the right, it's actually convex. And the reason these are 2 different solutions is because on the left in this coarsened mesh, these points along this joint, these intermediate points are actually located on the surface of the finer geometry, right? They're actually located off of that surface. And so technically, this panel right here at the side of this fuselage is no longer planar. This panel is not planar. These points in this intersection come up out of the plane. Whereas when I jump to that mesh directly, that coarse mesh directly, this panel is actually planar, and these panels are all planar, and so we get a different intersection. So that's probably subtle. It probably won't matter for you, but it's just to note that, you know, how we got to that model is a little bit different, and it does have some small differences that exist. So that was pretty much the presentation side. I'm going to go in and do a little bit of a demo for just a few minutes to just sort of show how working with this geometry stuff actually works. And certainly, if anybody has any questions in the chat, we can pop those up. And you know, finally, I'll just put a little bit again of the roadmap here. We're talking about the geometry updates here. And then Dave will go for the next hour where he'll talk about the solver in a lot of detail, and then I'll come back and do a bit of a tutorial. So that's kind of the arc for this talk right now. Okay, so very quickly, I'll just add everybody's favorite airplane. I'll add a pod and a wing and move that back. And so, you know, if we come into VSPRO now and you know, this GUI has changed from what you're likely familiar with. We'll talk more about that later. But without running the solver, if we just want to prepare to run the solver, this will just do the geometry and write the input file. So I'll just do that. We'll prepare the solver, and you'll see that right now in that first run, what we did, and let me come in and just delete the plane. There we go, clean that up. So here we have that n-gon geometry. And so if we change it to hidden, what we were working with was we did the analysis on the shown set, which would be equivalent. Let's change that to all. But we looked at everything thin. And so both the fuselage pod and the wing were thin. And we actually performed that intersection like I talked about before. And so we trimmed out those panels that would have been coincident here and did that intersection to get that geometry. To change that a little bit, let's take this wing and make it coplanar. Let's just pull it up a little bit. And in fact, let's make the root airfoil, let's give it some camber. Let's make it a 4412. And so that's just at the root, and we can prepare the geometry again. And this time what you'll see, since I moved it up and added that camber, you can see that it's a curved surface and it's now up off, and we perform that intersection. You'll notice that we also have to split this panel at the leading edge and at the trailing edge. We have to split it because otherwise you would have one panel that would wrap around the top surface and the lower surface, and that wasn't going to be good for anyone. So what we do is we find that leading edge and we split it down to make sure that we have two panels, an upper and a lower panel at that leading edge. And back here, you can barely see it, but there's a similar little split at that trailing edge. Also, you'll notice that I've highlighted in red, I've detected the cut-a condition. I've detected the trailing edges. And so now OpenVSP is finding the trailing edges and feeding those to VSPRO for it. So what I can do is I can come in, and in this case, I'm going to come to the pod, and I'm going to put that in set 0, and I'm going to come to the wing, and I'll put the wing in set 1. And if I want, I'm going to come into the set editor, and I'll come to set 0, and I'll change that name to thick. And I'll change the name of set 1 to thin. And what that allows me to do is I can then come here to VSPRO, and I can tell it on the thick set to use the thick components and on the thin set to use the thin components. And now when I prepare the solver, you can see we've done this intersection, and we have a thin wing with a thick fuselage. And so we've done that and trimmed it down and are ready to send that over to the solver. So we have a few other options. I'm not sure if these are going to make the release version. We can come in here and we can manipulate that n-gon mesh. I can triangulate it. I can, dump out some files, and I can, show whether the edges are manifold or not. I'm not sure if this will make it in. But for example, if you show those non-manifold edges, it's just doing a quality report where it's going in and checking that all of the normal edges. So basically any edge that has two faces adjacent to it is not highlighted. Any edge that only has one face is a boundary edge, and so that's in blue. And any edge that has three faces is shown in red. And so, along the wing, there's these edges that have, a top fuselage panel, a bottom fuselage panel, and then a wing panel. So those joints have three faces associated with them. Likewise, you can come in here, and these are experimental features right here. So at least in the near term, the refinement will not be in the publicly released version, not until we're ready to do something with it. But if I want to come in here and say do 3 refinements, I can prepare that geometry, and well, maybe that didn't work. Maybe I've got that turned off already. So yeah, I've got that turned off. So I'm gonna have to go back and fix that for Dave, but not for everybody else right now. So I'll deal with that later. Let me open up that model and just show the Cull orphans real quick, just so that people can see what I'm talking about on a real model. So here, and again, I'm going to get rid of the cutting planes on the center line just so that we don't have to look at that. So here's the model as it starts. And I can come in and you can see that this was very quickly put together or put together with the jury that protrudes just out of the lower surface a little. It's nicely buried in the upper surface, and then it pokes out the top of the wing. And again, the reason this was done was just so that the strut and the jury and the wing. There we go. Let's get rid of. Let's just do these, and we'll do them in camber. Let's see if this works. There we go. So if we look at them in a thin representation, you can see that if we were to do this intersection, they would protrude, and we would have these, dangling extra panels. And so that's what the Cull orphans option is all about. So that when I prepare that solver, we're going to go through and go ahead and we'll do that intersection, but then we'll trim and we'll throw away those little remnants. So we have that kind of an intersection that is more likely what you want in that case. So that's pretty much what I have to say about the geometry modifications that have happened on the OpenVSP side that then feed to VSPRO. Again, I'll do a demo of this version of VSPRO later. And in the meantime, I'll take any questions quickly, and then we'll turn it over to Dave to talk about the solver side.
All right, we'll let the chat catch up in, say, the 15 seconds or so to get everything caught up. But haven't seen any questions posted just yet. And we've got a couple of minutes here before we need Dave queued up. So we'll see if anybody has any lingering questions here in the chat. There's a couple. Okay, so Rob, if you want to address those, we'll see if we can't get switched over to Dave.
Yeah, so I see Andy asked, why might you want to do a mixed thick and thin model? And that's a great question. What I find is, number one, the thin solution is faster than the thick solution. You have half as many panels on lifting surfaces. You also, of course, the trailing edge, by definition, you're going to have a top and bottom panel that are very close together, and that can cause issues in the solution and in the solver. And by going to a thin surface, you get rid of those. So what I find is that for lifting geometries, for lifting surfaces, for wings and propeller blades, the thin surface often gives a better solution than the thick surface, and it certainly gives a better solution than you have any right to expect. It does a really good job. The thin surface does great. And but what I find is that it's sometimes unsatisfying when you work with a fuselage. Where that wing body join happens, representing the body as a thin surface isn't necessarily very representative. And for example, putting a nacelle downstream of a propeller the main thing that nacelle is doing is acting as a blockage and pushing things away from the slipstream. And so when you put that, if you represent it as thin, it's not providing that blockage at all. Whereas if you make it thick, it can provide that blockage. So in practice, what I will probably do is I will usually represent, like I've shown in this one, lifting surfaces as thin and non-lifting surfaces as thick. And I think that that'll, lead to more realistic simulations. Now, you followed up with the question about the thick surfaces like the fuselage produce lift or just moment. So right now, they only produce moment because they don't have a sharp trailing edge with a cut-a condition on them. And so they still only produce moment, just like a thin representation of that fuselage. There is something that I've been working on for Dave to put in a limited wake at the trailing edge of thick bodies so that we can pick up where is the tail end of a fuselage and, how do we represent that? And Dave's going to work on integrating that so that we have basically better lift carryover from one wing to the other, and also some ability to, put a separation point at the tail end of a fuselage back here in a way that makes sense for that model. So when that happens, when you start to put a wake on the back of a fuselage in some way, then yes, it will start to pick up a load. It'll carry a force, not just a moment. But without that, without a wake off of a body, basically the only place you're going to get forces is where there's a wake, and otherwise things just contribute to moment. I'll let Dave answer the question about thick components and supersonic analysis. I think that's something that he has some experiments with, but isn't ready to go yet. But I'll let him get a little bit more on that, and I'll go ahead and maybe answer any other questions in chat as Dave takes over the talk.
All right, thank you, Rob. All right, can you hear me? All right. Supersonic for thick sort of kind of works for me, but nobody else. So leave it at that. So what's new? We're going to go through a little bit of all the stuff that Rob's been talking about thick, thin. There's a bunch of other things in there. A lot of that's geometry. We're going to talk a little bit about the theory, aerodynamic formulation, armated multipole, and then some of the new stuff in terms of the Adjoint solver and optimization capabilities that we have. I'm just going to say that a lot of this stuff is kind of, by definition, going to be at a high level. We only have a half hour. I'm happy to take questions offline if there are any. So what's new? As Rob mentioned, we have full support for mixed thin and thick geometries. So before we could do what we call panel or the VLM models, now we can mix and match. There were some questions from Andy, why you would want to do this. Computationally, I think Rob said, basically the thin geometries, they're just numerically going to be nicer to solve, especially when you've got like a cusp trailing edge kind of things that Rob was hinting at. I think my real plus for being able to do thick, thin geometries is that at the conceptual design level, you're lucky if you know what the wing looks like, and you probably have no idea what airfoil you want to use, especially if you're doing things like a transonic airplane, where the thickness of the wing makes a big difference. And so if you ran the thick geometry and you'd have to choose, obviously, some airfoil to go with that, then if you were to do something like the transonic truss brace wing, the intersections there are going to make a big difference, depending on how thick those airfoils are. And we'll talk about that a little bit later. But if you do the thin geometries, then the only thing you need to worry about is the camber distributions, and that's interchangeable with the twist. And so I think it just makes the analysis at a conceptual level a lot easier when you just don't know a lot of things. New wake formulation. The wakes still act as streamlines if you run the code before, so they're all adapted with the solution. but they are handled in the solver as unstructured surfaces. So when you look at them, they'll look like streamlines, but under the hood, actually, they're all treated as surfaces that are adjusted basically to adapt as streamlines or stream surfaces. And this means that there's now a single unified multipole solver across both the body and the weight panels. When we did the fast multipole before, we applied it to the body. The weights, because of the way they're handled, we ended up with like a slightly different multipole solver for the weights. And this just unifies everything, and this makes it a lot more efficient, and B, just a lot easier to add new features. Next, basically we have a new fast adjoint formulation. If you've been following things, this is the second time I've done this. First time through, we used automatic differentiation. That actually worked. It turns out it didn't scale very well. And I can go into that if anybody has questions about why, but let's just leave it to say that it did not scale well with the multipole formulation for large cases. So we basically went in and hand coded all of the derivatives that the AD would have provided. We're still basically setting up the adjoint system of equations and solving that the same way we did before, but basically all of the derivatives that we needed to do that are done. We're coded by hand, and it was a lot of work, but it's really, really fast. It's fully parallel. And then building off the adjoint formulation, we now have an optimization capability that I'll talk to you about briefly towards the end. So geometries, they're defined by triangles, quads, and as Rob mentioned, general polygons. The geometries can be thick, thin, and they can be thick and thin. So you have your choice. You can do panel, you could do VLM, or you could do a mixture of the two. So this is the geometry that Rob had talked about, this generic truss-braced wing. Rob kept hinting that the intersections were at the truss and the wings were done hastily. They were actually done initially just so that you could actually get the intersections to work for the thin case. I'll just note that a lot of times, like if you model something up and you've got nice clean intersections for all thick geometry, if you then go in and choose the wings to be thin and run comp geom, you'll notice that you don't necessarily get nice clean intersections, because now the intersections are basically not thick, but they're thin. And so things that intersected when they were thick might not cleanly intersect when they're thin. So these are probably perfect cases for having different sets of parameters for extending the tips of the truss and whatnot so that they actually intersect when you want to do thin cases, and move it back when you want to do thick cases. So this is that generic truss-braced wing. As Rob said, we can now run this both thick or thick-thin. Rob always showed this similar geometry. Here we got the nacelles and everything in there. Again, it's up to you how you want to run this. My general suggestions were, if you're looking for lift, drag, and moments, do thick-thin. If you need pressure distributions on the lifting surfaces like the wing, if you need the pressure distribution on the upper and lower, then you're going to have to run thick. But you will have to run, it's basically doubling the number of panels on the wing. So the computational costs will go up. The equations tend to be a little bit stiffer, so that's going to take a little bit longer to run. So if you're at the conceptual design level and you're really just looking for forces and moments, then just all VOM might be good, but thick-thin is like in the places where I would start. This is just, again, the thick-thin case. It runs fast. Again, it's all parallel. It's the multipole, as I'll talk to, and this, on my laptop, it's relatively old now, Apple M2, running 6 cores. It's like 25 seconds. So as I was saying, why thick-thin? The thick for the fuselage is just, versus the cruciform option is just orders of magnitude better. You're actually going to capture the effect of the thick bodies versus the cruciform solution. That said, the cruciform option is still there. It's going to run faster, and depending on your geometry, it may give you a reasonable answer. It has in the past, and it will definitely run faster. As I said, thin wings reduce the computational time, often significantly. Thin wings avoid the issue of nicely fairing wings to bodies. We don't really have nice fairings. And so again, if you have a thick wing and you've got like a high wing or a low wing, that intersection with the body without having those fairings, you could end up having some weird looking pressure distributions, just oddities that could affect the lift and drag, depending on how, how we integrate the forces and moments. But if you go thick, thin, this goes away. Thin wings avoid the issue of not knowing yet airfoil thicknesses. A lot of times you just don't know what it is, especially if you're doing a transonic analysis on, something like a 737. You're going to be in drag rise. You know that you need some kind of a supercritical airfoil. And if you take it and run it in VSPRO, you're not going to predict that anyway because it's a incompressible code basically with chronometer rotate corrections. But you may end up with weird weird interference effects if you've got things like pylons and nacelles and stuff like that. So just reducing it down to just a thin surface just avoids those issues. And then quite often, thin wing solutions actually are closer to reality. When we do a thin analysis, we're ignoring thickness, but we're also ignoring viscous boundary layer effects in all these analyses. And quite often these two tend to offset each other. So it's one of those cases where two wrongs often make a right, sometimes make a right. In this case, more often not, if you just look at VOM solutions, the viscous effects tend to decamber the airfoil, and then you get the same effect by basically going with a thin airfoil. So a lot of times, you actually get a better solution for the wrong reason. So the aerodynamic formulation, as Rob said, everything's based on edges, and we basically are using this generalized VSPRO law. And this basically just takes compressibility into account. So beta squared is just that 1 minus m infinity squared. If you just looked at kind of standard VSPRO law, that the beta squared would be 1, and everything would just reduce down to what you would normally see. So VSPRO models the vehicle surface, including the wakes, as a list of vortex rings, and each ring's made up of vortex filaments, like shown here on the right. So those vortex rings, again, could be triangles, they could be quadrilaterals, they could be n-sided polygons, and they don't have to be planar, as Rob mentioned. So at a very high level, the solution process is basically, we're solving a linear set of equations where we're trying to basically, solve for the shape of the wake and apply tangency to all the panels on the body. So we basically loop over all the body and the wake vortex rings and calculate their induced velocities on all the other vortex rings, including on the wake. We enforce tangency, we enforce the wake surface boundary condition, i.e. we want to make them basically a stream surface. This gives us a large system of nonlinear equations because it's nonlinear because we don't know where the wake is. Or it's if we were to force the wake into a specific shape, say a planar wake, then it's a linear set of equations. But in general, we have a nonlinear set of equations. And then we have to solve these iteratively until we converge, right? So we've guessed at some vorticity solution, initially 0. We go through this process, we come up with a vorticity distribution on the surface and the wake that satisfies the solution for the guessed wake shape. We update the wake shape and we restart this process and reiterate until we're converged. And so for those who like to look at math, this is all I'm going to show. The linear set of equations that we're solving at each iteration, we basically have like 3 sets of equations. There's surface tangency equations, so that's as v dot n equals 0 on the body. We have wake streamline equations, so that's for each of the wake streamlines coming off the trailing edges. Those basically have to align with the local velocity. And then we actually, in the new version, I won't be talking about this much, but we have basically implicit stall equations. So basically the user can specify, for a wing what the local 2D CO max is, and that's implicitly imposed during the solution process. So it's not a post-processing thing. So when you solve these set of equations, it's possible that some station along the wing is stalled. That directly affects the cutting condition and globally affects the entire flow solution in terms of surface vorticity, the wake shape, etc. And so we have these three sets of equations for the vorticity on the surface, the wake shape, and the stall factors. And then the residual is just basically, that'll go to zero if we've satisfied the equations, right? So we're solving this one way or the other. There's two ways to solve this. Well, there's probably more than two ways, but there's two ways in the code to solve this. Fully implicit, so we can basically just solve that whole linear system of equations. So this is basically a Newton's method. So we have that Jacobian matrix times the correction vector equals, the residual on the right-hand side. And we can just solve that all directly, one big shot, and that gives us an update to the vorticity, the wake shape, and the stall factors. And then we still have to iterate. It's a nonlinear set of equations, and so we'll iterate on that until it converges. The other way, which is what we've had historically in the code, is basically what I'm calling the explicit method. And so we basically, in this, we guess at a shape for the wake, and initially that would be displanar. And so we'll solve the surface vorticity equations, assuming we know the wake shape, and actually assuming we know what the stall condition is. We update the wake solution using, that new solution that we just solved for the surface vorticity. We update the stall model equations, using the current vorticity and the wake shape, and then we repeat that. And that was basically the process that was in all the previous versions of VSPRO, barring the fact that we didn't have this implicit stall model. And so both these methods are now in the code. By default, it basically falls onto the explicit. That tends to be actually, in some sense, more robust and faster method, as I'll talk to. But the user can choose either one of these. And this is just showing a simple wing. So this is just a BOM or thin surface, wing that we've modeled. And I'm just showing the convergence histories. And so the explicit is there in cyan, and then is the implicit. And you can see that the explicit method, is taking on the order of 20 iterations, and this is, really deep convergence, dropping like 10 orders of magnitude. Generally, like 2 orders of magnitude would be sufficient. But even there, the explicit method is, taking on the order of, twice the number of iterations as the implicit method. But if you look at basically the residual versus time, you'll actually see that the explicit method is actually the faster of the two. It's converging, not quite twice as fast. And this is because the implicit method just has a lot more work per iteration. And so while it converges faster per iteration, the solution cost per iteration is higher. And I'll also say that using, basically Newton's method to solve these nonlinear set of equations, if you don't have a reasonably good initial guess, Newton's method tends to to diverge. So if you got a good initial guess, it'll converge fast quadratically if you're close to the root. But if you have a bad initial guess, it could more easily basically diverge than the explicit method, which tends to be just, albeit slower in terms of the number of iterations, but more robust. And so again, the default in the solver is to run with the explicit method, but the user can choose either. So agglomerated multiple, and this is kind of at a very high level. If you're familiar with vortex lattice or panels codes, you'll know that they tend to go scale computationally, like n squared wins the number of panels. And so if you double the number of panels, you're going to quadruple the solution time. So quite quickly, both memory and basically computing time will just kind of grow out of bounds for, most cases that you might want to run nowadays. So in this case, the solution is what we call multipole. And so we start off with the fine grid on the left, and VSPRO progressively creates coarser meshes in a magical fashion, where it's basically just merging those polygons from the fine grid to create a coarser grid, and then just recursively applying that process, so that we end up with coarser and coarser grids. And so once you have those coarser grids, we can basically apply the same, induced velocity calculations, but if a point, or more importantly, a region is far away from another region, we can evaluate those induced velocities on a coarser agglomerated grid, right? So if we're at, say, trying to calculate the induced velocity at the very nose of this vehicle from all the other panels on the vehicle, then those panels back there on the horizontal tail, well, there might be, hundreds or thousands of panels on the original fine mesh. A typical panel code would just have to evaluate all of those panels' influence to the panel at the nose of the aircraft. But if, in fact, we deem that that nose is far enough away from those panels back there on the horizontal tail, then we can use the coarse mesh to do those evaluations. And if you just look at that mesh, there's on the order of, a dozen panels now or less. So the net effect of this is that the computational cost will generally grow more like n log n instead of n squared. And the memory will also go like n log n versus n squared. So this greatly speeds up the solution process for large meshes, which is more than typical what users are going to run, right? So we're expecting to be able to run very complex geometries, not just a simple wing. So moving on, the adjoint solver. What we would like basically to calculate gradients of forces and moments with respect to the mesh. In the past, you could do this using finite differences. So if you wanted the partials of the forces and moments with respect to all the nodes on the mesh, well, if there's n nodes, then you have to perturb each node in x, y, and z, and then run the solver for that perturbed geometry, and then you also run it for the base geometry. So you'd have to run the solver 3n+1 times. With the adjoint formulation, you basically end up solving just the adjoint equation once for each force and moment component. So like F sub x, force in the x direction, force in the y, moment in the x, etc. For each one of those, you solve one adjoint solve, and that gives you all of the gradients of that force or moment with respect to all the XYZ nodes in the mesh. Again, this was all rewritten, basically hand-coded derivatives instead of using automatic differentiation. We were using the adept library in the past. It's full multipole enabled for the matrix transpose vector multiplies, just like it's, we do multipole for the matrix. Vector multiplies on the forward solve. It's fully parallel using OpenVSP. Adjoint solver by default just runs gradients with respect to the entire mesh for the inviscid, viscous, inviscid moments, and viscous moments. So that's 12 adjoint solves, and it tends to cost about 6 times a single flow solution. You also get free for all this, basically gradients respecting the Mach number, alpha, beta, PQR, so basically the inputs to the solver. And then if you've got control surfaces, we also get basically, the control surface derivatives, again, for free, because we basically know the partials of the forces with respect to a mesh change, and a control surface is just a mesh change. So all of those come out. So you don't have to, the old -stab option in the code, which basically used finite differences to do stability and control calculations for the derivatives, is still there. But if you run the adjoint, you get those stability and control derivatives out for free. And then just what do the adjoint solves look like? But again, at a very high level, that matrix we talked about before, that Jacobian matrix, you basically take the transpose of that. You're solving for the adjoint variables, so psi, for the tendency, wake, and the stall equations. And then the right-hand side is basically the partial of the force that you care about or the moment respect to, those variables, so T, W, and S, which, the basically the vorticity on the body, the wake shape, and the stall equation and nodes. And so this is a linear set of equations. It's not nonlinear. It's you just solve, boom, one shot. And with this and a little bit of math, you get the partials of F with respect to all the mesh nodes in one big shot. So how are we doing on time? Okay. So for a simple weighing, this is just showing, basically we do a forward solve with 12 adjoint solves to about 1.6 seconds. Again, that's on my Mac laptop. You want to do finite difference gradients. It took about, 560 seconds. And then the plot here on the right is just showing basically the total derivative of the force in the X respect to a perturbation of every node in X, right? So you go through every node in this mesh and perturb it in X by a small amount, run the finite difference, calculations, and you get you a gradient. And that's how the finite difference was done. For the adjoint, it's just one shot. So, it's 1.6 seconds versus 560 seconds. And again, this is just for the force in the X. The adjoint gives you out, force in Y, Z, and moments in X, Y, and Z as well, for basically within those 12 adjoint solves for, less than 2 seconds. This works for unsteady. I haven't talked about that, but the code still runs in unsteady, so you can do props. Again, this is just a simple rotor. We ran it like 2 revolutions. We use the adjoint to calculate the gradients. Again, this is just the force in X respect to a change in the mesh nodes in X. Finite difference calculations takes 4,100 seconds. It's like 7 seconds using the adjoint solve. Again, for the finite difference, you have to run, an unsteady solution for each one of those points, right? So you're running the baseline case, and then you're perturbing it. I'm actually doing central differences, but you're perturbing each mesh node, creating a new mesh, running that mesh, full unsteady solution, and getting the answer back out and doing finite differences. Or you could do the adjoint, and it's obviously a lot faster. So running out of time, but still the next person's time. So VSPRO opt. So basically, we've taken all of the geometry work that Rob's done, all the work that we've done for the adjoint, merged those together to create an optimization capability within VSPRO/OpenVSP. So we've directly tied to the OpenVSP API via C++. We use the adjoint solver for calculating the gradients with respect to the mesh. Currently, we do finite differences for calculating the mesh gradients with respect to the OpenVSP parameters. And then you do chain rule there to get the final gradients, right? So if you want you want the partial of CL with respect to an OpenVSP parameter, you just do chain rule between those those 2 sets of partials. You have a choice of a conjugate gradient or BFGS optimizers. All the inputs basically are on the .vspro file for those of us that like to run on command line. Rob is working to add all those into the GUI. We have support for thick, thin, and thick-thin geometries. And as I mentioned, Rob's working on the GUI integration for this. So that at some point will be released, but the code is all going to be there. So at worst, you could run it from the command line. So this is back to that truss brace wing. I toss the tails, toss the nacelles just to make this run a little bit faster. Basically, there are 53 design variables, 33 wing twists, 20 strut twist variables. I constrained CL to be 0.65 and basically trying to minimize CD. So the plots on the left there are basically the history over 10 iterations of the optimizer. So CL starts up around 0.7-ish. Again, I'm trying to constrain it to a CL 0.65, so you can see it's getting close there. I should mention that it's basically using a penalty formulation, so it's kind of getting as close as it can. You could up the penalty value and probably push this a little bit closer to 0.65, but it's like it, within a few percent of the constraint. CD has basically been dropped down, from 023 down to 018, right? So huge drop. OFD has gone from 30 to 35. I think that's all interesting, but what's more interesting is what it actually did. So the initial wing and initial strut are the dash lines here. Obviously, the fuselage is sitting in the middle. And you can see basically, I mean, this all had zero twist initially for these, both the strut and the wing. The strut was actually, unloaded. In this case, it's basically doing negative lift just as the initial geometry. What the optimizer decided to do is basically unload the wing, load up the strut, and if you stand back and look at it, you can see why. It's basically trying to come up with an elliptic distribution for the net lift over those two surfaces. So if you add up, the solid lines for the wing and the strut, you're going to get something that's very close, or at least as close as it could get to be elliptic-ish. Again, this took 14 minutes using 6 CPUs on my IM2 PowerBook, and then it's using the BFTS. And then just showing the optimized versus the baseline. So you can kind of see where it's twisted the wing. I should note that I'm holding constant the places where we have intersections with the truss and the jury strut. And that's more just issues with, like, if those components move, the intersections would no longer be valid. And so I need to work with Rob on, I think we have a way to fix that. But right now, basically the airfoil sections near the intersections were just held. We didn't optimize those. But you can see basically it's loading up the strut and doing its best to unload the wing. So I don't know if we have time for questions, and then it's pretty much on time.
Yeah, Dave, you're the next talk, so
yeah, I know. So I don't know if we want to.
So yeah, we can flex. Do you have the YouTube chat up? Can you see those, or do you want me to read you the questions that we've had?
You'll have to read them to me.
Okay.
So we're gonna go ahead and.
So I'll back up a little bit. We did have a comment about, I'll just say, I'm looking forward to VSPRO actually converging and not crashing in the future. Haven't been using it since it was so flaky. Thanks for the updates. Do you want to address that in any way?
Yeah, I mean, it crashes. I mean, honestly, I think, part of going to the thick thin, I think will solve a lot of issues. I think a lot of the issues we had before, backing up. I mean, some of the things I would just say in general when running VSPRO is that more panels isn't always better. A lot of times I'll get models from new users and they've basically refined the heck out of the wireframe, right? So there'll be, literally, 100 span stations, 200, points in the airfoil direction, on the chordwise direction. It's like super, super fine mesh. And even if it does run and converge, it's going to take forever. So start with a coarse mesh. The second thing is, with the VOM models, the way we had with the Earl G-Gen, and Rob mentioned this, we had overlapping surfaces. The code did its best to try to deal with those overlapping surfaces, so like a V-tail overlapping onto a cruciform fuselage. It tried to deal with those the best it could. Best practice would have been to basically by hand trim out that vertical tail so it doesn't overlap the fuselage for the when you're doing the VOM analysis. But now if you run basically even the thin, but if you run the thick thin, all those intersections, all that trimming is being done by Rob. So the model that's going into VSPRO is, from a geometry standpoint, a lot more clean. And so I think, that'll help convergence in general. The other one is, I mean, people don't always look, but you do want to worry about the convergence. So, I mean, if you're running more than one, if you're not running a fixed wake, then you need to check and see if the wakes are converging. And depending on your model, that may take 3 or 4 iterations. It might take 20. Like on this TTVW geometry, 20 iterations, it's dropping residual, almost 2 orders of magnitude. But on a simple wing, 3 or 4 iterations would be more than sufficient. So that's kind of on the user to make sure that things are converging. You can run the code with fixed wakes. If you're having problems, that's a good place to start. Just basically set the wakes to be fixed. It's a linear set of equations. And if you're still getting issues, then you can hopefully at least get a solution to see where in the geometry, maybe it's an intersection somewhere weird that is causing you issues, and you can cook that up.
I think that helps, Dave. We've also got a question. There's a CD naught result in VSPRO. Does it make a difference between its thick and thin?
So it will make a difference to some extent because, well, let's see. In the new version of the code, the CDs are only basically the CD naught, basically the viscous drag, are only being kept for the lifting surface. The goal with Rob and I is to basically merge the capabilities that are already in OpenVSP, to do when we're doing the wetted analysis, wetted surface analysis and all the drag buildup, is to make use of that for, that CD0, except for the wings, although you could still use it for the wings if you decided that was more accurate for your case. So right now there's a drag buildup, the CD0 viscous drag buildup for the wings. That's based on the local 2D CL, at each span station on the wing. And it's currently kind of basically hard coded to like a curve fit to Nakadomo 12 data. And so on the list of things for Rob to do is to basically, and we've kind of worked on this, is come up with a parameterization for any airfoil, and that will be in the GUI one way or the other, and VSPRO will get that, and so you'll be able to basically, just like you have a family of airfoil shapes, you'll have a family of airfoil arrow data that will be fed into VSPRO, and it is basically would be CD versus CL kind of tables, if you like. So back to the original answer, the lift distribution for the vortex lattice versus the panel will be different. And so that 2D spanwise CL will be different for those two models. And so CDO will come out different.
Could you speed up the convergence time using a grid sequencing approach like an overflow, where it begins an initial solution on a coarse mesh and then moves to a finer mesh as the solution progresses?
You could, and I had a version of the code that did that before I rewrote everything. So yeah, I mean, you definitely could do that. There was one point where I had a version of the code where you could choose which agglomerated mesh to actually run on, right? So by default, it basically runs on the finest mesh, but you could choose which mesh to actually solve on, and then I would have basically do grid sequencing. It helped sometimes, didn't help other times. It was one of those things that could be kind of touchy. And so I tend to lean on things that are going to be more robust. And so, yeah, it's definitely like something you could do. I think really what you'd want to do is something like a full multi-grid. And then, you've got to decide if you want to do that at the nonlinear or at the linear side when you're solving the basically the Jacobian delta equals minus residual. You could basically do that over the multiple grids, or you could do it at the nonlinear level. So it's open source. If somebody wants to go and do a full multi-grid version of the code, more power to you.
All right, one more question before we let you go on your second part. Can you also constrain something like pitching moment as you run the optimization?
Yeah, I'll show an option. I have a simple demo that shows that, but yes.
Great. Thanks, Dave. Go ahead and carry on into your examples talk.
Right. How do I get out of this? There it goes. All right. So I'm just going to go in and just going to show this geometry to begin with. So this is going to be like the demo geometry, a couple of different demos here, but just going to run this basically in VOM mode and talk about the adjoint, and then ultimately I'll show you some optimization results on this as well. So it's just a simple, Hershey bar-ish wing. So it is what it is. So if you go in, and Rob had mentioned, right? So and I know he's going to go in and talk to this. So I'm not going to speak too much about the GUI, but you have thick set, thin set. So when I talk about the optimization later, the optimization is going to be driven by this, what you've chosen here. So whatever set you've set is thick and whatever set you've set is thin, that's what the optimization is going to look for, right? So you have your choice on, you could set everything to thin, everything to thick, or mix and match. And the optimization basically will read in that your VSP3 file, and it's going to look for what you set here when it starts running OpenVSP. So I just wanted to, we're just going to run this stuff. And so I don't know if that showed up, it was so fast. But basically, that was just running that model in VOM mode. It ran out, 9 iterations until it decided it converged to 10 to the minus 3 on the max residual, and it took 0.2 of a second. So if we take a look at the solution, it's going to point out some of the stuff that's going on. So obviously we have the pressures, we have the initial computational mesh that Rob mentioned that he's generating. In this case, there's no intersections, it's just a simple geometry, single wing, single component. But there's the computational mesh. Rob kind of alluded to it. There's still an underlying triangulation that he provides. So like when we write out, pressures and things like that, if you're to import those into your finite element solver, stuff like that, we'll export those out on a triangulated grid. So even though we're possibly solving on a grid that has, n-sided polygons, we can export that to a triangulated surface for other users. We got the trailing lakes here, which is kind of a boring case. They're actually adapted here. There's just not a whole lot going on. You can draw them as points. And then, as I alluded, they're actually under the hood being treated as surfaces, right? So each one of what would have been, vortex filaments before coming off the trailing edges, they're still, mathematically looked upon that way. But from the multipole solver and everything, this is all basically a surface just like the surface of the wing or the bodies or whatnot. It's just that the boundary conditions on the wing are tan C, the boundary conditions out here on the wake are basically that each one of these is a streamline, so it's a stream surface in the end. And then if we start, there's only 2 levels here of coarsening, but you can see the initial grid there, and then the coarsened grid was that. Same thing with in the wake, it basically just did a single level of coarsening. It was a pretty coarse grid to begin with. But again, the agglomerated multipoles working not only on the body, but also on the wake. So that was running the solver. You run the adjoint on the command line. It's literally just -adjoint, and it just ran it, and that took 1.1 seconds. So about, I said 6 times longer, but it was on the order of 5 times longer, really. So it basically ran, inviscid forces in X, Y, and Z, inviscid moments in X, Y, and Z, viscous forces and X, Y, and Z, and the viscous moments in X, Y, and Z. So it solved those 12 adjoints, and the original solve has to solve the equations initially. And it did that all in just about 1.1 seconds for that simple case. And again, if you were to run this using finite differences, using central differences, it was on the order of 600 seconds. If you were okay with one-sided differences, I guess you could cut that down to 300 odd seconds. But we're still talking orders of magnitude speed ups in terms of calculating the gradients. And so if you look at what's written out, running that adjoint is there's a file, and you can access all this stuff through an API, obviously C++ with the solver, and that's what the optimizer does. But if you just wanted to get stuff into a file format, that's all written out. So this is node 1, the XYZ location node 1, and then all these columns, and there's a lot of them. This is the partial of the force in the X respect to a change in X for that node, respect to change in Y, change in Z, change in, all of those. That's the total force. Then we go over here, we have the total moments, then we have basically the inviscid forces, we have the inviscid moments, we have the viscous forces, and then we have the inviscid moments, right? So they're all there. And it took about a second to run. So that's it for the VLM. I don't know if we want to take questions as we're going, Rob, or just do it at the end. It's Rob's. So the next one is just maybe thanks to Rob. It's basically this geometry. It's just basically a canard, wing, pod, tail geometry. But in this case, we're going to run thick and thin. So thin for the wings, thick for the fuselage or the pod. So we'll run this. So this dropped about 2 orders of magnitude for the L2, not quite at 1. I'd probably run it out a little bit more, but if you look at the forces and moments, they're pretty much converged. But if I was doing an optimization, I'd run this out a little bit further. I should say that took 4.5 seconds on this, right? And so that's solution. Throw up the wakes. Again, this is basically a thick body with thin wings and tail, adapted wakes. Now, one thing I'm going to use this one to talk about, so if we look at the computational mesh and we kind of look at what's going on with these wakes, one place that'll throw the solver up is the location of the first wake line near an intersection. And so we don't have direct control over where this first wake line will be. It's just shed all the basically span stations on the wing. The next span station was inside, so it got trimmed off. But if we had increased the number of span stations or changed the diameter of the pod, this intersection become arbitrarily close to the body. And strictly speaking, the code should work, but numerically that becomes difficult for it to converge. And so the wake can tend to do weird things, especially initially when it's iterating and I'm trying to figure out where the wake shape is. And so the wake might actually, initially go inside the body, which is clearly wrong, and then it may pop back out from the body. And so it may, converge, given enough iterations, or it may just oscillate back and forth from inside to outside the body if this is arbitrarily, it's arbitrarily close. And I say arbitrary, it kind of depends on the geometry and what you're doing. And so, move that first point, some reasonable distance, and reasonable, again, is something you just have to play with, away from the edge of the body. That doesn't mean that that portion of the wing isn't carrying lift. The cutting condition is still being applied on that trailing edge segment that goes from the wing root intersection out to this first filament. It just means that the weight is not being adapted until this first filament. But you can see, in this case, it's adapted to the shape of the fuselage. And, it's moving up over the top of the over the canard is weight's moving over the top of the wing. Everything as you would expect it to do. All right, so the next one. Actually, I want to move to this one first. So again, this one's going to be, let's go ahead and bring it up to mind, is this geometry here. And so again, Rob's still working on the GUI for this, so all this stuff is done by the command line. But in the code, you basically can set up an optimization, set the number of optimization iterations, number of 1D search directions, a couple of other convergence parameters, and then you basically have weights for the penalty formulation for the optimization. So I've got a weight on CL of 1, a weight on CD of 1, and I want a CL of 0.55, a CD required of 0, right? So it's trying to essentially minimize that. In this case, it's basically a constraint that we want CL to go to 0.55. And then we have a weight on CMM, right? So the pitching moment. And the pitching moment required is 0. So we want this thing to trim. So you could set that to something else, right? So if you had, you had a propulsor and you wanted to counteract the moment that you're getting from thrust, right? You could set this to some other value for the pitching moment that you calculate, and it would drive it to that, with knowing that, in the final analysis, that the vehicle would be trimmed because you have some other device that's generating, a moment. So I'm going to go and all right, so I'm going to basically run this. So it's going to start this optimization off. And then hopefully you can see this. Basically, this is just going to show what it's doing as it's iterating here. So it's running this optimization in the background. It's already done 4 iterations of the BFGS. It's trying to drive CL to 0.55. It started off around 0.44. It's trying to minimize CD, but right now it's trading off that to try to get CL. And then it's trying to drive the pitching moment to 0. So it started off like at minus 0.32, and it's, you can see on this plot, it's essentially driven it to 0. So now it's going after CD. It's going to run like another iteration or 2. All right, it's done. So it ran 16 iterations. You can see CL is basically pretty much dead on at 0.55. It's dropped CD, it's higher than it was originally, but CLs are higher than it was originally, but it's basically trying to minimize CD for that given CL. And we've constrained CM to be 0, right? So if you look at what this is plotting out, this is the history file. So this is the iteration, this is the CL, CD, all the forces, and we can see that we started off with a CL of 0.44. Over 16 iterations, it drove it to 0.549996. I mean, you could tighten up the conversions if you wanted to. The drag, went from 2128 to 2412, but again, the CL has gone up. So presumably that's the best it could do to minimize drag for that given CL, as well as force the moment to 0. So we started off with a pitching moment of minus 0.3, and we've driven it down to 0.005, right? So it's essentially 0. And again, if you're not happy with that, you could tighten up the convergence. But this took just about 60 seconds. This was running on 6 processors on this M2 Mac. Forward solve time was like 40 seconds. Adjoint solve time was like 12 seconds. And then geometry updates was like less than 7 seconds, right? And so there was like 238 forward solves, 96 adjoint solves, and then 293 geometry updates. Finally, take a look at this. In the output from all this, it actually goes through, and there's 238 solutions. These are all the solutions that were run either, as an adjoint, precursor to an adjoint, or basically during the 1D search steps, once we had the gradients or the search directions. So this is just the initial geometry. You saw this before. We can start stepping through this, and you can see the optimizer is basically like playing around with the sweep and the twist, right? And ultimately, the changes get smaller and smaller, and that's the final shape. I should say that the center of gravity is actually right at the nose center line, right? So it's forced to come up with a shape. It needs to throw some of the lift up front in order to trim. Otherwise, it would never be able to drive CG equals 0, right? So you end up with a bird-like wing. And then
Hey, we got
you
a
can
question here online, what the design variables in that optimization were.
Yeah, thank you. Yeah, in this case, I didn't go into this. Rob will talk to it later, but basically this is just using the design variables that you can pick out, within OpenVSP. So it's a .des file. So I was remiss in not noting that in the talk. But basically, we've got the sweep, we've got the twist, we got the dihedral, and then I'm not using the root chord. So it's just basically these first 27 for this optimization. So we've got 27 design variables, sweep, twist, and dihedral at every one of the span stations.
And then we also had the question, could we add tracking of those to the history out file to watch the convergence of the design variables?
Yeah, it's written. Yeah, you can. I could add it to there. I think I'm going to add it to a separate file, because then it's going to become a really huge file. I haven't decided. Right now, I'm just basically, I write it out. It's commented out. I just write it out to the screen and take a look at it. But yeah, that is definitely one of the things. What will also be in there is that I'm, right now it writes out a final. So, and I plan to do this at every iteration, but it's just doing it now for the final iteration. But like we have this, there's the original, so we can go up into, and there's design variables, you can load, and the wing.des is this original wing.des. So, these are the initial values here. So like the sweep was all 10 degrees, the twist and dihedral all 0. But we can open up the final one that was written out, and so boom, that's the final set of parameters. And so like we can open that. I call it. Can't type. Right. So there's.
Great.
The final one's right there. So I think
Great.
I'm out of time.
Well, let me give you a few more questions. is in this case, was the optimization's objective function CD, was that only CDI or was that also CD naught? Was it total?
It was total.
Okay. And then
yeah, I mean, within the API, right now with the you could do anything you wanted. So if you just wanted CDO or CDI, right now it's assuming totals for VSPRO opt. If you want to go in and write your own code and use the API that's available, you could choose any subset that you want. And this could actually be like a lot faster because it's actually calculating like all the moment gradients. So you could get rid of, the moment gradients that aren't pitching moment related and speed up this process. Right now, it just does all 12 gradients, whether or not your objective function actually needs them. It's honestly pretty cheap, but you could speed things up marginally.
Great. How can you use alpha as a design variable?
I mean, we calculate. I haven't actually tried, but we do calculate the partials of all the forces and moments with respect to alpha when you run the Adjoint. So that's available in the API. So I was actually thinking about that yesterday, trying to like what would a rational way to be to expose that within VSPRO opt, So I was more thinking like user might want a specific CM alpha or a CN beta and be able to size, say for CN beta, size the tail for it, right? Just like in the same thing, maybe sizing a horizontal tail for a CM alpha constraint, right? For a static margin kind of thing or something like that. So I'm open to suggestions on what a good objective function would be. But all those gradients are there, and so we could certainly use them to do something like that. And again, they're all available through the API. You'd have to write your own code. But if we could come up with what are kind of usable cases, then we could add those in to the VSPRO opt capability.
So we've also had the question or suggestion about adding the moment reference location as a design variable.
Yeah, I mean it does that already. That one's like a freebie because it doesn't really matter, right? So it actually calculates that as well. But yeah, we could do that.
And I'll just add some context here. Obviously, Dave's talking about this in with respect to an optimization problem, and he's working on this general optimization problem. But we're also, in the back of our minds, we're working on thinking out how would we formulate a simpler trim problem so that we can, in the long future, when we have all this stuff done, I hope to have a GUI in OpenVSP where you can choose your design variables and do optimization of VSPRO to an objective function of your choice, but also have the ability to specify trim problems that mathematically it'll be basically the same, but you just won't choose a whole bunch of geometry design variables if you're just trimming the vehicle. So that's all in the realm of where we're headed with this.
Yeah, because I mean, with this and respect to like one thing we can't model right now is an all moving control surface, right? So like if you want, which I really want, and Rob knows I want. So, but like with the trimming thing, right? Like if you run the adjoint, we can calculate, CL and CM respect to alpha. And so we could set up a system of equations, to solve that, for, the user wants a certain CL and wants CM equals 0. So that'd be two equations, two unknowns. But then when you start adding in more control surfaces, then it becomes an optimization problem. But we could do that within this formulation, right? So you could have the user, I want it to be trimmed. I want, not just changing the shape, but I want you to have these two control surfaces, figure out how to trim the vehicle so that CL is whatever, CM is 0, but I also want to minimize drag, right? And that we can do, right? It's just more like being able to easily set that up for the end user.
Awesome. Great, Dave. I really appreciate it. I can't stress how excited I am about all this stuff. I was watching you do your demo with a giant grin on my face. So,
yeah, I just want to toss out because you spent so much time on it, and it's not getting a lot of use. Is the multi-level NGON stuff? All right, what I want to do with it. I mean, I know Rob mentioned we could do a grid adaptation, so that's definitely one thing we could do. But the other thing we could do is actually with the adjoint and with a finer mesh above whatever mesh you're solving on, we can actually estimate errors in the forces and moments based on the solver errors, in terms of the discretization. So there's this whole theory of weighted residuals. So we basically solve the flow solver solution, we solve the adjoint solution, we interpolate that stuff to a finer grid, do some magical math, and you could come back with estimates for the errors in CL and CD and CM, right? So like we could run the code and not only just give you CL and CD, but give you an estimate for the error in CL and CD, which then you could use to propagate through other uncertainty analyses. And I think that would be very useful and very powerful.
Absolutely. Thanks, Dave. I'll maybe if you stay on the Zoom call for a little bit in case more questions come in. People are really excited about it in general. Interesting work.
Sure.
And the last comment was just, being able to understand elevator deflection to stay in trim across the CG range, and then trim required for different flap settings will be great. So I think we're all thinking along the same lines here. So I've got for the rest of this up until we do our West Coast lunch. I don't have slides. I just was going to do a little bit of a tutorial type demo of using VSPRO in the new setup. And so you've seen a bunch of this just picking up and looking at the case I did before, but we'll come back and again we'll add everybody's favorite airplane and bring this guy back here. So we've got a pod with a wing, and I'm going to go ahead and I like to look at it in hidden usually because that just declutters. I'm going to increase the resolution on the span a little bit here. And as Dave said, right here in this case, I chose something with a really narrow spacing. I ended up with something with a really narrow spacing of that first panel. I'm probably going to get away with it here. I'm going to push my luck and see if we get away with it. And the reason it's easier to get away with if you're at the part where the fuselage is ducking away, is sort of diverging, it's in the aft half of the fuselage where it's going away from the wing. Whereas that case when he showed the card where it was way up on the front, that's where the fuselage was still getting wider. That's really makes it a lot more sensitive. Although that said, this panel running right here with these really thin panels, that's probably undesirable. So we'll see how that works out. Just for fun, let's go ahead and I'll make it a little bit better by just lifting this, the Z of this up. So there we go. I got rid of that by just lifting it up some. And like I did before, I'll come in and make this a 44 something airfoil. So there we go. We'll make it a 4412. And I'm going to copy this at the root and we'll make it a 4412 out at the tip. So there we go. We've got that. Maybe a little bit lower so that if I did do a thick, it's still fully buried. There we go, something like that. We've got a shoulder wing. And while we're at it, let's go ahead and let's add a vertical tail. Turn that off, rotate it about the X for 90. And then we'll bring it back here someplace, put it on the back end of the airplane. And then we'll come in and bring the span down and then bring that root cord down. There we go. Maybe make the span 2, make that 2. There we go. That's about right. And we'll dial that back a little bit. So we'll just deal with this as a starter for our aircraft. I'm not going to be like Brandon, who the smart thing would be to save all the time. I'm just going to fly without a net, and you'll get to watch it crash, and then I'll have to make another model. and we'll just live dangerously. So again, I'll set up a set with thick, and I'll set up a set with thin, and then I'll come in here to my wing and I'll say, okay, that one needs to be thin, and the other wing needs to be thin, and my pod, I'll make that thick. So again, this is how I will run most of the time, about like this. I'll come into VSPRO, and in terms of setting this case up, the main thing I need to do is tell it to use my thick set for thick and my thin set for thin. And everything else here right now is just at default. We're going to run 3 angles of attack. We're going to run 3 wake iterations with 8 wake nodes. We're not running the implicit solution. We're not doing anything fancy there. The reference, moment reference location, or my reference values, here's something new. On the wing, on the plan form, I used to just calculate this sort of average chord, which was an arithmetic average chord. Sometimes it was meaningful, sometimes it wasn't. But we had the request to actually go in and calculate the true MAC using the MAC definition. So now I actually calculate the MAC as well as what I call the curved area. So that's going to be the same as the area if you have a straight sectioned wing. But if you're using blends, if you have a lot of planform blends in your wing, then the area that's reported here on this slider is going to be the theoretical area of the trapezoidal wing without the blending, whereas this curved area actually finds the true sort of projected wing area, including those blends. And likewise, the MAC includes those blends. So yeah, so back over here, what we're going to do is, and let's give these names so that we at least know that this is the vertical tail, and the wing is my wing. So I can use that, and I'm going to come in and say, let's grab my reference lengths from the model, and I'm going to take it from the wing, and I want to use the mean aerodynamic chord, and I'll use the standard trapezoidal reference area. So that's my reference conditions. My reference location right now is about 000, so that's the nose of the aircraft. And, you know, we're set. This is enough. I've got lots of cores here, but we'll just run with 4. And, you know, this should probably work. We'll just run the solvers, see how we do. And there we go. Everything ran through, and we've got some load distributions. So first, let's just go look at the geometry sum. We'll turn this to hidden, and you can see we did that thick thin intersection all around, and we have, you know, what we expected, including the vertical tail. The reason these artifacts are happening is just because OpenGL, we're drawing this cutting plane directly down the center line, and it's exactly overlapping with that vertical tail. So that's just the way it is, because we're drawing that right on top of it. We could move that plane and that artifact would go away. We were in 3 angles of attack, so we got 3 load distributions. We can look at the sweep, so we've got a little bit of a drag polar building up. I'm actually still hacking on a bunch of this stuff because the file formats are changing, with especially for propellers and unsteady stuff. So I'm not going to click and spend too much time here on our Y data, but you can see I'm actually plotting the load. So CL is lift coefficient times the local chord divided by CREF. So that CL times C is what you get to get a local load, and you can also plot the CL distribution itself, the lift coefficient. And we get a lot of users who sometimes get confused about which one they want to look at. So typically you want to look at little CL if you want to think about how close is the section to stalling. How hard is that particular wing section working? And what you'll see here is this configuration is actually prone to tip stall, because we're hitting the highest local CL out on the tips. So those are going to stall first, all else equal, and that's probably undesirable. So we'd want to twist this or otherwise change the design. Whereas when you look at CL times C, that's looking at the load distribution. So that's the total force. So the CL out here is multiplied by a smaller chord, and the lower CL in the inboard is multiplied by a higher chord. So we're getting something that looks, you know, elliptical-ish. So when you're designing a wing, you definitely need to look at both of these. You can always come in and look at launch the viewer, which pops up on the wrong screen on my computer. So we come in here to the viewer, and you can see just the geometry, you know, is what we were talking about. We've got this mixed thick thin. I'll go ahead and I usually turn on the pressures. Now there's something a little bit weird that is of note here, and Normally you might think that, when you look at a pressure distribution, you should have a nice smooth, the same pressure here on the side of the body is happening here on the top of the wing. But we're not actually plotting pressures here on the wing, right? The wing doesn't have any thickness. And so the wing is plotting delta CP, where that's delta CP from the top to the bottom surface. Whereas the body is plotting CP because it knows CP on the surface. So you're not going to have, like if we come in here and we show the function type and we draw lines, you're not going to have, perfect transition of these contours from the wing up onto the body, because we're actually plotting two different quantities. It's not as drastic as plotting pressure and temperature, but just like plotting pressure and temperature, we're actually plotting two different quantities, and that's why you'll see a little bit of a jump. So you just need to know that you have delta CP on the thin surfaces and regular CP on the thick surfaces. And when we come in here and we turn on, the contours, you have to apply your own context, right? We're using the same color bar for delta CPs as we are for CPs. All right, we can come in and we can turn on our trailing wakes, which again, this is a pretty boring case. We're looking at the 0 alpha right now, so we can change our case up to look at the, at the higher 3 degree alpha. And here you can really see, right, we're not seeing blue up on the side of the fuselage, and that's because we're plotting delta CPs here and CPs here. So we are getting a hot spot there at that trailing edge a little bit, where probably changing that paneling would help resolve what's going on here at the root quite a bit. On the other hand, one of the other things that was pretty unavoidable when we would do a thick surface solution is you get a lot of hot spots out here right at the wing tip. And Dave and I have some ideas that long-term we may be able to help fix that. But that's another great reason that the thin surface solution is so great, is that trailing edge tip hot spot pretty much goes away. So not a lot else to show here, or we could, but I don't want to belabor it too much. Here's that computational mesh, again, showing the n-gons, and using minus, I can do the agglomeration like Dave was saying. There's 1, 2, so there's 2 levels of agglomeration, 2 coarsenings here on this particular case, or we can go back to the fine. And then, as we said, we can also show the triangulation, which, again, this isn't used for the solution, but this is passed along for visualization and reporting loads, just because so many other tools need triangles and, can't work with my fancy polygons. Okay, so that's enough viewing on this case. Let's go back. And just for fun, let's look at it if we wanted to do it all thick. So I'm going to just change the thin set to none, and I'll change the thick set to all. And we can just run it again. And so here we're running what we previously have called a panel code solution. But again, in this case, it's with n-gons. And so if we look at it hidden and we come in, we've got really very clean intersections because we don't have any of those nasty triangles. We've cleaned all that up. And what I really wanted to do is come in here and show the viewer again, just so that we could see the difference. If I come in again, this was 3 angles of attack. So here's the 0 alpha, and go ahead and show the trailing wakes and go up to the 10 degrees. And so now you're getting what you might have expected in terms of that smooth blending of pressures from that body onto the wing and on all the surfaces, right? So now you're getting that kind of transition of pressures that you might have expected. And if we were to look at this with line contours, you're going to see, they're not black. Okay, we'll turn it upside down. So you can see that those contours, they travel relatively smoothly, right? They're continuous from the wing up onto the body. So pressures transfer that way. So that's just something to keep in mind, that if you're ever, if you show one of your CFD colleagues your pressure distribution and they wonder, why do you have this jump at the wing body joint? The reason is because you choose to. So that's just showing you that real quick. In terms of other things, let's go back to our thick-thin setup. Most things in here aren't changing. Some of these GUIs moved around, like the reference area used to be over here on the left. So I've rearranged some of these so that more of the basic setup is together, and some of the wake settings are now more together. So when Dave showed the wake and we look at the convergence, we're coming down here for the different angles of attack. We've got fix in. Let's just be crazy and let's run it for 20 iterations just to see what it does and show convergence. So there we go. That's 3 angles of attack. So if you compare this to the publicly released version of VSPRO, convergence behavior is definitely greatly improved. Dave first went and did that implicit formulation, which was more expensive per iteration, but converges faster. And then he went back and competed with the explicit and made it better too. And this improved convergence was really driven by the optimization workflow. When your optimizer is trying to change things by 10 to the -6, you need a solution that's converged deeper than that. Otherwise, your optimizer is just going to go off into la-la land. So a lot of this work that he's done has gone into making this convergence deeper and more reliable. So before, the solutions were good in terms of, an engineering perspective on forces and moments. The solutions were fine, but they weren't deeply converged the way that an optimizer was going to work with. So, we're getting much more, much deeper convergence is now possible and probable with these kinds of cases. So that's something worth looking at. And we can go more into it, but there's options here to either freeze the wake after a certain number of iterations. You can go strictly to a fixed wake, and that's what you can do for a simple case like this. The truth is if we come in and if we look at our load distribution and if we look at our forces, if I run this case with a fixed wake, it's going to run really fast, and it's not going to look any different substantially, right? This is a simple case with pretty straight wakes that aren't going to make a huge difference. So definitely keep fixed wake in your pocket, something to run. On the advanced tab, we come in and we have, a bunch of additional settings that, frankly, you probably need a lot of these less than you maybe did in the previous version. But you can come in, there's this stall model that Dave didn't talk a lot about, but he mentioned that there are now stall equations in that giant matrix that he's solving as the coupled set of equations. So stall is now, it's included in the solution in a more realistic way than it was before. And you can turn that on or off here. And so if you turn it on and then you dial in what your 2D CL limit is, it'll then start dialing that back. So let's just do a quick demo. Let's come to our load distribution. Let's see what CL is here. It looks like it's coming up to almost 1.3. So if I want to limit that to 1.15, so we can turn that on and set this to 1.15 and run this solver again. And this is, again, with fixed wake, so it'll be real fast. Although the fixed wake is probably not a good test of it with the, let's go back and run it with a relaxed wake on this. So there we go. And so you can see the load distributions change some, particularly outboard where we've limited that stall. And you'll really see it if we come in and look at just the CL distribution. So here we've come and, we've capped that at that 1.15. And before it would limit that locally when contributing the local load, but it wouldn't propagate that into the trailing vorticity from that local section. And now that trailing vorticity from that local section, if you were to come in here and, and you look at this solution in the full 3D sense, and we look at that high angle attack case, oops. When we do that, the wake out here where you're hitting that local CL limit, that wake is reflecting that reduced circulation and it's being flattened out. And so that's bringing that down and affecting that. And consequently, because it's reducing that circulation in the wake, and it's reducing the circulation on this local section, right, it's influencing the entire solution. So far away from that, the entire solution is affected by that local CL limit. I see a question online that is it applied to all the lifting surfaces? And the answer is yes. If I put this into a large amount of beta, it would apply that stall, that limit to the vertical tail. Right now, you as the user, you just dictate. You wave your magic wand and you tell it what the CL limit is. And that right now, that CL limit is applied globally to all lifting surfaces, whether it's a propeller, a vertical tail, or a wing. In the future, Dave talked about how I'm working on a way to improve the tunability and the way you can customize the airfoil model for drag. We're also that'll give us the ability to set CL max across wings and across components separately. So you would at that point be able to dial in a different CL max on a per surface basis. Okay, so that's sort of the stall model. In past VSP, let me throw some control surfaces on this wing. Let me come over here to subsurfaces and add a control surface. So here's a control surface, and lots of things have changed. We can now use ADA to specify the span-wise extent and whatnot. So that's kind of nice, is to be able to dial that in with ADA instead of just U. So there we've got a control surface. We can come back to the GUI, and the easiest thing to do is just auto group, all surfaces. So what we've done is we've added these. We now have a wing subsurface, and if you look, there's a little icon out here showing that the right-hand control surface is positive trailing edge down. That's what that rotation icon means. Whereas the left surface is going to be positive rotation trailing edge up. So that means that if we apply just a straight, note one deflection on both of these, it's going to be like an aileron. So these gains, you can come in, and if you wanted it to be like a flap, you just change that to be 1 - 1, and those gains would then make it like a flap. We can leave it as an aileron, but you can come in and you can do any control mixing you want. And so here we can come back to our overview, and what we have here is what deflection do we want to apply to that control group. So let's put in, say, a 5-degree deflection, and again we're doing thick and thin, and so we can run that with thick, thin. And here we go. And so it's admittedly fairly ugly to our lift distribution, but you can see we've got control surface effects in here. And if we come into the viewer, let me bring that back over. We now have control surfaces that are going to show up, and they'll be a lot more clear. And I think we can show them deflected. Where is that? Maybe I'm missing it. Dave, am I crazy here?
They should have deflected already.
Okay. Oh, they are deflected. You're right. Well, no, then yeah, they are. They're drawn deflected already. Sorry. So yeah, so that's showing the and if we come in here and show the computational mesh, there we are showing these intersections and how we're capturing that control surface deflection. So that's but that's with thin surface, which is sort of quote unquote always been available. But if I change thick to all and thin to none, and let's just run one angle attack, we don't need to run all of these. If I run that at 10 degrees and I run that solver, what you're going to see is going forward again in this dev version, we now have the ability to have those control surfaces modeled with a thick wing. So again, we really recommend, most people are going to be really well served using the thin formulation. But one of the things before that forced that was whether if you wanted to deflect control surfaces. And so now with the new update, you can put control surfaces on thick stuff too. So let me change that back to thick thin. And that's me running out of time. There's plenty of other, most things are going to be similar. There are other things that are different. If I add a prop to this model very quickly, and put it out on the wing, something like that, and on that prop, let me just move it back to, there we go, closer, something like that. Let's start, if you put it in actuator disk, you no longer have to tell it that you want it to be represented in the disk. It does need to be in one of the sets that's in the analysis. So right now, that actuator disk is not going to be included because it's not in any of these sets. And so let's go ahead and we'll just put it in the thin, and you'll see the disk option just popped up. And so now you can come in and you can set your parameters. And in the past, you always set either RPM, thrust coefficient, and power coefficient. But now you have the choice where you can choose what you want to set. So you can come in here and you can instead, if you want to set the dimensional thrust and the propeller efficiency, then you can come in and say, okay, my propeller efficiency is going to be 0.9. And in whatever units this model's in, I want 100 thrust at 2000 RPM. So now it's a lot easier to dial in these settings. And if we run that solver, it's going to have that actuator disk. But one thing that we can do now is, let me copy that prop, and we're going to paste it. And this one, I'm just going to move to the other side. So now we've got two props, one on each side. But now I'm going to represent this one with blades. And so what this will allow me to do, and again, it's in the thin set, is when I come to the advanced tab, I now can talk about, well, if there are blades in here, how do I want them represented? And static blades, that means, you've got a jammed engine and your props aren't turning. So that's not what you want. But you can either do unsteady rotating, and there's also now a new pseudo-steady rotating mode. And Dave can talk more to that, but this is a new formulation that is an approximation, but it's really good in a lot of situations. So let me turn that to pseudo-steady, and let me come in here and increase the number of wake nodes. And you need to increase typically with a prop because I have to actually tell us how far it's going to go back. And I'm going to get rid of the control surface just because we don't need it at this point in the model. So we're running thick thin with a thin rotating prop and with an actuator disk. So we're going to run this, and we're just doing one angle of attack at 10 degrees. And, there's a lot going on there, but let me just launch the viewer and bring this over. And what we have, we just did an unsteady simulation. Let me show pressures and trailing wakes. Oh, wow. So that's definitely screwed up. So I need to fix that. We'll pretend like this worked. But the idea is it's supposed to... oh, no, that was pseudo-steady. Interesting. Well, the point I was hoping to make was that you can actually now mix and use, and this has never been a solver problem. This is always a GUI problem, but you can run a solution with both an actuator disk and a rotating rotor. And sort of my use case for that is, some kind of a compound helicopter where you might want to look at rotating unsteady blades of the rotor, the horizontal rotor, the lifting rotor, with an actuator disk for your propulsors on it. So I'll save this case now. Now that it's a bug, I'm going to save this case and get that fixed. But anyhow, I've gone well over my time, and we need to get to our break, and I need to get to lunch. So thank you guys for that demo, and I'll try and answer any questions on the show up in the chat.
Okay, thanks a lot. Appreciate the demos, appreciate the time. Andy just asked if we can run actuator disks in a duct. I believe we can.
So you can in terms of the solver, but I don't know that I believe the physics, right? The way the actuator disk formulation works is it's an analytical solution to an actuator disk in isolation. So and by solution, what we mean is you specify the strength of the actuator disk, and it tells you the velocity induced by that disk everywhere in 3D space. So we basically add that to the right-hand side of the solution, and then we leave that fixed, and then we solve the panel strengths everywhere else in order to satisfy the boundary conditions. So this works pretty well. It's essentially a one-way interaction. The actuator disk interacts with the airframe, but the airframe doesn't interact with the actuator disk. So this works really well for something like a prop out on a wing, where the slipstream of the prop is not really significantly changed by the presence of the wing. However, if you had a prop over a blown wing where you were deflecting that slipstream and you expected the vena contrada to turn by 40 or 50 degrees, this isn't going to capture that turning. So I think I would do a lot of tests with a actuator disk in a duct to see if I got reasonable solutions. But the presence of the duct is really there to change the area of the vena contrada, of the slipstream coming out of the actuator disk. So the duct would, you wouldn't capture that change. So I would try some tests and see if you got the results that you liked. But I think it's probably, I'm skeptical of how that would turn out. There's certainly, on our back burner, Dave and I have ambitions that he's done some work on a transpiration boundary condition that would allow you to have an inlet on the front face of a nacelle and an exit on the back face of a nacelle. And if we put those together with some proper wake treatment, I actually think for a potted turbofan engine or other jet engines, that would probably be a better solution than an actuator disk and a duct. So it's not it's not on our list of near-term things to do, but it's definitely something that we're thinking about. Okay. Well, thanks everybody. I will see you back at in about 25 minutes, and we'll continue on talking about landing gear.
Thanks a lot. We'll see you in 30. All right, everybody. It's 3:30 Eastern, 12:30 Pacific. We're going to go ahead and get going with the next presentation. I'm going to make sure that everything is being recorded again, so for anyone that needs to join or come back and watch later, you're more than welcome to. You know, we've got an international community here, and the time zones aren't always friendly. So, Rob, you are welcome to proceed.
Thanks a lot, Brandon, and thank you everybody for sticking with us. I hope you're enjoying the workshop today. I was just chatting with Brandon offline that today is really a look at what's to come, and these things will all hopefully be released soon. But as opposed to other presentations other days where it's been more about the current state. So hopefully this is as exciting for you all as it is for me. So earlier today I talked about just sort of a general introduction about the geometry analysis and auxiliary geoms and landing gear and how those work together to create a bunch of a capability. And so now we're going to circle back around and we're going to, retread some of that information. But this time, since we have that context, we'll be able to dive a little bit deeper and things will make sense. So to start with, what you may ask yourself, why add an explicit direct component landing gear model in OpenVSP? And so there's a lot of good reasons in my mind to do this. First and foremost, there's a lot of analysis we want to do with a landing gear. And if we just use a generic stack or a generic other component, then we don't know, quote unquote, in the computer science way, we don't know that that's a landing gear. So by making it a landing gear component, I can build real intelligence, not artificial intelligence, into the model of how it is. Also, I'll just say that having a credible landing gear solution adds a lot to a conceptual aircraft design. I've seen a lot of aircraft designs over the years where people have spent many, they've killed many CPU hours in the pursuit of their design. And you look at it from the back of a room and you're like, yeah, the landing gear doesn't work on that at all. There's no solution that airplane balances and can take off and land. And, the more you get into a design, the more that matters. So having a credible gear solution adds a lot. And then what I was really trying to figure out here is okay, what can I add without adding too much complexity? We want to capture the design space and the importance of the gear, and we want to capture what it does to the airplane. But at the same time, at this point, I don't want to put a full kinematics engine into OpenVSP. And so there was a big debate that I had about how am I going to represent the landing gear? What is the right representation? And, when I think about it, the analysis that I want to do, i.e. the verb, what I want to do with the landing gear, determines the modeling detail. What I want to do determines what I need it to be represented. So, for example, if I want to do ground handling, then I need to know the contact points. What are the contact points on the ground? If I want to do tip back analysis, I need to know, where the wheel axis is, where the bogey hinges, and I need to know the static tire radius. If I want to do rollover analysis, I need to know things like flat tire radius, inflated radius, and the strut expansion and compression to do that kind of rollover. If I want to do packaging of the landing gear, well, then I need to get more into the gear mechanism design. And, spoiler alert, we're not doing that yet. We've decided we're not going to do the packaging. But then there's a lot of different sort of levels of detail we could go for. I could just do landing gear, could have just been a ground plane and 3 contact points. And that could have been the landing gear model, right? That would have been a start. We could start to model the tires in the down position, maybe up and down position. And maybe we start to put in the strut and the bogey in terms of some of those things. Then we could go further than the strut and the bogey to include secondary struts, different pushers and things like that, and actuators, all the way to things, the real nitty-gritty details like the up locks and down locks and how does the real mechanism work. So, I debated a lot of these things and, what was appropriate at a conceptual design level. What I came up with, and then there was also this debate that I had with myself of, should I come at this with what I call sort of a top-down model, meaning we start by taking a strut and we attach it to the aircraft at a trunnion, and then at the end of the strut, we put an axle with wheels on it, and then from wherever the wheels go, we then determine where the ground plane is. So that's a top down. We go from the airplane down to the ground. Another alternative is what I call the bottom up, where we first define the nominal ground plane, and then we position the wheels on it. And you may or may not even need a strut then. But if you did, the strut would then go up and, maybe it would connect to the airplane, maybe it wouldn't. Or maybe there's sort of a middle out where you start by positioning the wheels in 3D space, and then the ground plane is intelligently figured out where that is based on where the wheels are. And again, what do you do with the strut in that case? So there's different pros and cons to these. And, it comes back to sort of what we talked about with a routing geometry the other day about, the update sequence. How does OpenVSP update a model, and what does that mean? What does this mean for attachment and all these things? So the TLDR, I went with the bottom up. So we used a bottom up approach for the landing gear. And right now, there is no strut in the model. I have some ideas that maybe someday we could add that. But for now, maybe this is going to be surprising, but the gear doesn't retract and it doesn't have any struts. So the general approach is that we have, and then there was also the choice of, do we want to do with separate geometries? One geometry for the main, one geometry for the nose gear, one geometry for the ground plane. And do we model all these separately? Or what we went with is a combined. So we actually have, it's sort of this combined component that's all the landing gear in one. It's based on the ground plane, but it also contains all of the different bogies and all the different tire definitions. So that's that combined approach. So I went with a combined approach from the bottoms up, and we left out the strut is sort of the decisions that I've made. So in the gear component, there's the design tab, and if we were to talk about starting with the transform tab, what the XForm tab of the gear component really is controlling is the ground plane, the nominal ground plane. So this is the idealized, where's the ground in relation to your model? And the XForm tab positions that. And when you go from there, then you come over to the design tab and you start adding bogies. You start adding groups of wheels and you position them in XY on that ground plane. So you're positioning them where they are on the ground. And you can also specify the Z above ground. So if you have something like a U2 or a B52 where you've got an outrigger that's out on the wingtip that does not normally in the nominal wings level position, does not normally touch the ground, you can do that. You can have your gear that touch the ground, and then you can have other gear that don't touch the ground. So we've got this, fundamentally it's a ground plane representation. We can either automatically choose that size where it'll choose how big of a ground plane to draw based on the size of the model, or you can dial it in yourself if you want to tune that. And you can also decide whether or not to draw that ground plane. All the analysis works whether the ground plane is drawn or not, and no matter how big you have it. The analysis is independent of that, but just for visualization, you can control whether you want to see the ground plane or not, and whether you want to see its extent. This component needs to know the units of your model. And the reason is because tire designations are given in inches. The standardized international standards for tires are given in inches. And so if you're going to specify a tire in inches, then for me to draw it in the right scale, I need to know what scale your model is. So we do that right here. You tell it what units your model is in, and then you can specify your tires in inches and everything will work out. And then the last thing that the gear actually has is it has a full CG envelope. So the min, the max, and the nominal CG position in both X, Y, and Z. And so we're going to draw that as a little box with a dot in the middle. The dot's the nominal, and then the box shows the limits. And importantly, right, this is not calculating the CG of your model, right? We have a mass properties calculation that if you go and spend a bunch of time and you specify the densities of all your airplane, it'll do a bottoms-up calculation from the geometry of what the CG must be that matches that. This is the opposite of that. This is I'm the conceptual designer and I dictate my CG needs to be here, right? We're just waving a wand and placing the CG. And we're also therefore defining the envelope. So there's no math that determines this other than you dictating where the CG is. But we need to know the CG in relation to the gear in order to do those tip over and tip back type calculations. Okay, so that's, how the overall gear design. Then we drill in and we talk about the bogey design. And so you can place as many bogeys as you want. Usually you'll have two, a nose and a main, with the main being reflected symmetrically. So you'll end up with 3 contact points. But if you don't want the mains to be symmetric, you can do that. You can drop them from that. If you want to have more, like a wide body, like a A380 or a 747, where you've got multiple main gear, you can add multiple main gear. You can add bogeys like a B-52 or whatever. So you can, you add your bogeys, as many as you want. And then you dial in the configuration, which is how many wheels across and how many wheels in tandem there are. And so in this case, I'm showing a 2-2. And if you weren't aware, there's an FAA designation, a standard for that a 2-2 is actually represented for a 2 duplex. And so the configuration up here, I actually write that. I write a 2D. So there's a 2 duplex, or if you go to a triplex or whatever, a quad, this configuration represents that FAA designation. So then you can dial in, the spacing between them, either side by side or longitudinally, whether you want to specify that as a gap or a dimensional distance between them, so you can dial those things in. You dial in the position of the gear relative to the ground plane. If it's a steerable wheel, you put in the maximum steering angle. So if your nose gear can turn 90 degrees, you put in 90. If you can turn 20 degrees, you put in 20. Your mains, you'll leave that 0. The strut deflection, it's a very, very simple model of strut deflection. All it is a direction vector, a magnitude of compression, and a magnitude of extension. And that's how we model, in this case, how you specify what the gears travel and the strut compression and extension is. It's just a vector and a magnitude in each direction. Same vector, different magnitudes potentially. And then we have limits, constraints on the bogey rotation. So if your gear has a maximum, say the bogey can only rotate 10 degrees, then you can put in here and you can put in that plus or minus 10 degrees for the bogey rotation. And when I'm doing the calculation for things like the tail strike, if the tail strike angle is greater than 10 degrees, then the bogey will rotate for the first 10, and then it will rotate about the wheel's axle until it finds the tail strike. So it'll do all that geometry to figure out when the tail strike happens with that kinematics. Okay. So that's how we lay out the bogey, and then we can talk about the tire. And so what I did for the tire is there's a professional society called the Tire and Rim Association, and they set the standards for tire nomenclature and how people talk about tires and a lot of other things. And you can search for the Goodyear or Michelin tire handbooks. So this one, I don't remember which one I grabbed this from. It looks like the Michelin man in the corner. So they'll publish PDF files with tables of tire data, and that's all based on a parametric geometry description. So I went ahead and I paid for basically copies of the standards for the Tire and Rim Association, and I used that to build a parametric model of the tire that matches the TRA's documentation. And it's completely massively overkill, but it was a lot of fun. So I actually have the rim curve here and the tangency of the tire hitting it. It's completely over the top. So that's always fun. So on the tire, you choose which bogey you're editing, the active bogey, and then you can put in the tire designation. And typically that'll be in inches. You'll put in what the diameter and the width of the tire are in inches. If you don't want to work in inches here, then you can work in the model units. And so you tell it the model units instead. You tell it the ply rating. This is only used for the grown wheel dimensions. We could talk about that as later. So you can put in that ply rating, or it's used for this sidewall detail shaping it. So it doesn't matter much. You can play with it if you want, but it's just there. And then you dial in the rim parameters. The diameter of the rim the width of the rim is a part of the designation. The diameter of the rim is a part of the designation. So what you see up here, this is 44.5 by 16.5-21. So that's a 44.5 inch diameter by 16.5 inch width by 21 inch diameter. So here on the rest of these parameters, we have, instead of just two options, you can either specify them in inches, which will match the data from the handbook if you're looking something up. You can specify them in model units if you really want to stick to your model units, or you can specify them as a fraction of either the diameter or the width. And so for most of these parameters, in particular, this 0.77, 0.82, 0.88, and down here, the 0.35, these are very representative numbers that are non-dimensional that are going to represent a lot of tires. So for the most part, you're really only going to want to change diameter, width, and diameter of the rim, and dial those in to match your tire. And the rest of these, I mean, you can tune them if you want, but mostly these non-dimensional settings are good. Okay. So that's all about setting up the nominal ground plane and the nominal landing gear definition. We then need a whole bunch of different kinds of auxiliary ground planes. So these are, again, used by the geometry analysis for setting up these off nominal ground plane positions. They also, if I have a landing gear with 3 contact points, I need to tell it, well, which contact points, which axle am I rotating about when I do something like, my tail strike calculation. So I have to tell it which points we're rotating about and what's the off nominal state of that gear. And so that's what these auxiliary ground planes are for. And in the auxiliary geom, I'll show you that in a bit, you have the choice up here where you can choose many different kinds. So rotor tip path, rotor burst, and then we have 4 different landing gear types. We have 3-point ground plane, 2-point ground plane, 1-point ground plane, and then we have the 3-point composite clearance envelope, which is that interesting aircraft carrier one I talked about. So you choose your type, and what you see here is the different analyses that they're used for. So if you're doing the 3-point ground plane, that's what's used for the ground and steering clearance, the weight distribution, and the ground maneuverability. The 2-point is for the tail stripe and the tip over and the tip back. The 1-point is for that roll clearance when you're on one wheel and you're seeing whether you hit the nacelle or the wingtip first. And then finally, the 3-point composite clearance envelope, that's its own, it's a 3-point, but that's that aircraft carrier one. And now each bogey then, if you have 3 bogeys, you then have the ability to come in on each one. You tell it which contact point. So you pick for an auxiliary geom, you say, oh, I want to use the nose and the main, and I want one contact point to be the 0 symmetrical copy and the other contact point to be the 1 symmetrical copy. So you set that up, and then you can tell it on the suspension. Do you want the suspension to be nominal, compressed, or extended? And then do you want the tire to be nominal, extended, grown, or flat? So these are different states for the tire. And what's amazing is for a simple tricycle gear that is a symmetrical tricycle gear, there end up being 720 possible off nominal states that gear can take. So there was really a sort of a combinatorial explosion that we're trying to handle by setting up these auxiliary geoms. So you dial that in that you want, and then you go and you add your geometry analysis. And so there's a bunch of different geometry analyses, and each one of these then needs a specific auxiliary geom, and it needs specific primary geom as well. So the yellow ones in this list, this is a table of all the geometry analyses currently in the development version of VSP. And the yellow ones are what we're interested in right now because they're the landing gear associated ones. And so what this table means is, for example, if you want to do a tip back calculation, then you need to tell it a 2-point ground plane. And this is the tip back from the CG. So it knows then the 2-point ground plane, and it knows the CG from that landing gear, and you don't need any secondary geometry. So it can do that tip back calculation knowing just the 2-point ground plane. If you want to do the tail strike angle, then that's going to be, you're checking interference with the plane, you're checking interference with the ground plane with a 2-point pivot point, so 2 contact points on the ground, 2 landing gear, and then you're finding that angle. What's that tip back angle? So the plane 2-point angle is another analysis type. The primary geometry is what's the geometry you're trying to find a collision to. So that's going to be the rest of the airplane, and that can be a mode or that can be a set, but it can be that geometry. So that'll be that any type is the primary. And then the secondary is going to be a 2-point ground plane, right? So basically this table tells you, and everything should make sense when you understand what it's doing, that, a weight distribution, you need to know all 3 points on the ground. For the sideways tip over, for the tip over maneuverability, you need the nose and the main contact points. So all these dial in what geometry information is fed to the analysis. And as I talked about earlier, there's a whole bunch of gear-related geometry analyses. We've got our tail strike angle, we have our CG tip back angle, our tip over angle, our ground maneuverability, our roll strike angle, and then less familiar to people, maybe the composite clearance envelope. And so if you want to specify what is the envelope that you're interested in, that's a special separate text file, which looks like this. And all it is just 2 columns of X and Y data. In here, I've started at -1,000 and come across and then specified out what these points are. And when you read in this file over here, you actually have to tell it what units the file is in, because just like everything else, now you're bringing in something with dimensional information into VSP, which is normally non-dimensional. And so in this case, my file over here is in inches, and that's what I know my clearance is in, but maybe my model is in feet. And so I have to tell VSP, yes, I read in this file, but then that file should be interpreted as if it's inches, and then it'll be scaled properly. And then we have this definition of the main gear offset for it being imperfect. And that becomes a surface that we can check. And so while that's up, I'm going to go ahead and fire up and do a little bit of a demo. And anybody has any questions, please go ahead and ask them in the chat, and I'll try and address them as best I can. And actually, before going to the transport, let's start with an empty model. And we'll start by just adding a landing gear. And you'll see that when we first add a landing gear, all we have is a ground plane. So, we start with a ground plane. As I said, its position, its origin is wherever it is in the transform. So I'll move it around in a minute, but right now we'll just start with it at the origin. So we have a ground plane, and as I said, right now we're automatically sizing it, and without anything in the model, we just size it to 10 units, and we're drawing it. If I don't want to see it, I can turn it off. My model's in feet, and of course my tires will be in inches. And my CG, I haven't specified any CG yet. So it's all just 0, 0, 0. And that's that gray spot right there at the center. So if I want to add a bogey, I just come over here and I add, and in this case, we'll give it a name. We'll call it nose. I didn't have a name at first, so let me rename that. So this is now my nose gear. And I want to move its contact point forward. So we're going to bring that out to say, we'll call it -10. That positions that nose gear. And, I can come in now, and I'm showing it pretty coarse, just like anything else. I can increase the tessellation to make that look a little prettier. I can come in here, and if I want, 2 or 3 or 4, however many wheels across in that landing gear, I can do that. And then likewise, now you wouldn't normally do this on a nose gear, but, if you wanted 2, 3, 4, however many wheels in tandem, you can dial that in. So we'll do 2 across and 1 in tandem. And then, like I mentioned earlier, we can either talk about it in terms of the gap of the spacing is a gap. So how far apart are these in terms of a gap? Or, we can do it either fractional or in model dimensions, or we can talk about the center distance. What's essentially the pitch, the distance between centers of these. So, if you're reading off a print, you may have that read off as a center distance or whatever works for you. Okay, so we've got, our contact point. Right now, our compression direction, that's what this green line is in the background. This is showing me, spacing gap of 0 is a little bit little. The compression travels, so that's showing me where my compression would go. So this is the bogey pivot point, is that center point there. And if I compress the gear, it's going to move that all the way up to here. And likewise, the extension, if I extend the gear, it's going to move it all the way down to there. So this just depicts, and if I move, for example, if I change that vector, right, I'm dialing in some X component to the vector. So I'm just showing, how does the, what is the unit, the direction vector of compression and the magnitude there. And that's visualized with that green line. All right, I'm taking way too long here. Let me just go ahead and add in another bogey for my mains. And you can see it's back here. Let me give it 2 across and 2 in tandem. And let me move that, out in the Y contact point. And then in this case, I'm going to want to say that it is symmetrical. So I've got a button here to say it's symmetrical. So now I have a typical tricycle gear. So that's what adding a landing gear is like. We can come over here to the tire. And again, on a per tire basis. So here we are, we're on the nose bogey. We can say, what, that's too big. This is only going to be, say, a 10-inch tire. Oh, I'm missing it. Sorry, that is the main. Let me rename that. Sorry, there we go. So in fact, we don't want that to be 10. We want that to, say, be 20. So we can dial in and change that size and, dial in the tire size. And I will say, notice when I'm drawing this, notice the tire sticks a little bit below the ground plane. And that's because the nominal ground plane is what we draw. The tires are all drawn at the static loaded radius with respect to that ground plane. Okay, so that's how we set up a nominal landing gear. What we can do then is we choose that landing gear and we choose an auxiliary. And when I add that auxiliary, I then have to come to the design tab and I choose what kind of auxiliary. And obviously, a rotor tip path is not a meaningful auxiliary for a landing gear. So in that case, we're going to come in and say we want to use a 2-point ground plane. So this would be something we'd use for like a tip back angle. So we choose, or let's start with a 3-point. So we're checking clearance with the ceiling. So we choose a 3-point ground plane and it immediately draws what is that off nominal plane. But we want it defaults, right? We have nose gear. So we want to make this nose, and then we want to choose the main and the other main and the other symmetrical. So now what we have is if I show only, I'm now drawing the off nominal landing gear. And you'll notice its tessellation is different, right? It has its own tessellation control if I want to make that fine. It has its own tessellation control. But so this is now drawing the off nominal landing gear. And so I can come in and I can specify what's the state of any of the gear. So let's take this landing gear and say it is now compressed. And so now you can see that it jumped because the left gear was compressed. And we can make the left tire, say, flat. So that means it's going to ride on the rims. And so that's how you can control what an off nominal gear state looks like. And if I show them both, you can see, how that movement is, right? So we have the nominal gear position and then that off nominal. So that's what you do to set up and use all of these. Again, I'm behind schedule, but let me jump over to the transport model that has all these things set up already. And what we can see here is, right now, I'm only showing the nominal gear, right? And for all these auxiliary geoms in this particular model, I'm not actually, like my 3-point ground here, it's also everything's nominal. So now I'm viewing it, I still have everything nominal and static load, but I needed this, for example, this 2-point ground mains. Let's just, let's show that one. And let's turn off that other one. Come on. There we go. Turn that one on and let's turn off the nominal. So notice the nose gear is gone, right? That's because the 2-point landing gear doesn't have the nose gear in it. And so this is just the main. So then this is what we're going to do that tip back calculation about. And again, I'm running out of time, but if we come back to the geometry analysis, the way you set all these up is you add one to add it. That's going to show up as default. You need to choose the type. So in this case, we want it to be a planar interference with an angle about a 2-point rotation. So that's plane 2-point angle. And so then we're going to choose our primary geometry as, say, the airframe as a set. So we're going to compare it against the airframe. And then our secondary is going to be this new, what do we call it? 2-point ground mains. So 2-point ground mains is going to be what we rotate about. So that's what we do to set up the tip back. And then we can evaluate that. And notice it already did it. it calculated that tip back. And notice we have some options down here because we were rotating in, by its sign convention, the counterclockwise direction. So if we wanted to rotate the other way, we would calculate about that, and we would see that in this case, this geometry is going to hit the nacelles first. So that's its rotation there. So that hopefully gives you an idea of how you set up the main landing gear, the auxiliary landing gear, and then the different geometry analyses. I'm going to delete that one. And hopefully you're going to have to go back to the slides, I think, and look at that table to make sure that you see how things map in terms of which analysis you need in which case. But I think it should make sense. Everything, has to be the way it is. And so if you understand what it's trying to do, you should be able to see and think through the process. So I know that's been a bit of a fire hose and fast, but I'm going to try and stay on schedule and jump back and then talk about the rest of the geometry analyses. I do see a couple of questions. Can I do a geometry analysis against a propeller and a ground plane? Yes, you can. So I can maybe demo that in a bit. And Brandon, if it's okay with you, I'm just going to transition directly into the next.
Yep, sounds great. You're all queued up. Go ahead.
Great. Okay, so we've talked about the overview of geometry analysis. I did a little bit of a deep dive about landing gear. So now we'll go back and we'll talk a bit more about all of the analyses and the auxiliary geometry that goes with it. So here, I've got my table of geometry analyses, and now I've highlighted all the ones that don't have anything to do with landing gear. So that's the yellow ones are the non-landing gear. And these are a little bit more flexible than the landing gear ones, right? The landing gear ones have a very clear purpose, whereas these are much more abstract, right? If you want to check whether two things collide with one another, whether two things interfere, then you're doing interference checks to see if two things interfere. So these are very, very flexible. There's several geometry analyses to do different kinds of interference checks, and we'll talk about these. And most of these work with any geometry type. So in some cases, we'll have different behavior if there is an auxiliary geom or a particular geometry type. But for the most part, these interference checks just work with any old set. There's also the visibility stuff that I'll show, and that'll be really fun. And then I'd say this is the beginning, right? I expect there to be more of these geometry analyses added in the future. There's a lot of use cases. I've tried to capture as many of them as I can in the time I've had to do this development, but we have more ideas. So expect more of these to be added in the future. So there's that I talked about earlier, that problem that we have of organizing all of these analyses. You have to set them all up and get them to work. And how do you organize them? So that's the whole purpose of this geometry analysis manager. You've now seen me use it 2 or 3 times. Up at the top, we have this browser where we can browse and name and interact with the different analyses types or the different analyses in our model. We can name them and specify the type down here. We tell it the primary geometry group and the secondary geometry group that it's going to work with. Any options for those that have options are down here, and then sort of the go button. The analysis and control is down here at the bottom. And you also use this to visualize and look at the results or interrogate the results. You can click the show results button, and when you do that, it pops up this results browser. And so this is sort of an inspector. For example, the point visibility analysis, it doesn't just calculate a single scalar, it calculates a whole bunch of different quantities. And so all these quantities are then shown in this results browser. And you can come in and you can click on them and you can look at them like in a spreadsheet, or they're all available from the API. So if you're using this from an MDO framework or some other design framework, you're going to want to query these things from the API. Now, the first kind of simple geometry analysis is what I call external geometry analysis. So we're checking external interference. And what that means is that the two geometry groups, they are supposed to be mutually exterior to one another. So these are two things that are supposed to be outside of one another. And what I'm going to do first is I'm going to perform a full comp geom on both the primary group and on the secondary group. And that will trim and create the OML of each set. And that includes if you've used negative geometry. So if one of the geometry groups includes negative geometry, this will capture that when it performs that, essentially that comp geom on both geometry group. And you can see on the right, I just have two elementary spheres. And since they're supposed to be external to one another, and unfortunately they overlap, when they overlap, I actually generate the mesh. I calculate that volume of overlap. And so you can see in red, it shows when two things collide, I show you that. Now, I didn't want to just calculate, simple metrics. So what I actually calculate so that you can use this in the design process is a combined interference metric. So in the case of an external geometry analysis, if the two bodies are outside of one another, external like they're supposed to be, right, I calculate the minimum distance between them. And I actually, in this combined metric that I'm talking about, I put it in as negative. So the negative minimum distance. And if you're an optimization person, you're familiar with putting constraints in negative null form. And so negative constraints is good, right? That means they're satisfied and you're very happy. So since it's the nearest distance, that also tells you sort of how far away you are from that constraint being violated. If it's a large negative number, you're very safe. And if it approaches 0, then you're approaching contact. Now, when they intersect and they overlap, what I do is I then change the metric, and the metric becomes the volume of the intersection normalized by the reference volume. And the reference volume is the volume of the smaller thing. So that volume of intersection then becomes, once you collide, right, we go from a negative value, we come down to 0, then we come and as we intersect, we have a positive value, and that positive value gets larger the more they overlap. And again, this is to give a gradient-based optimizer a direction to solve this collision so that it can push back against this collision. And then finally, there's the case of, well, what happens if it's completely swallowed? What if it's completely contained within the other object? Now you would have the problem that if you just use the volume, that volume, no matter where it moves around, it's the same volume, right? So it's not getting any better or worse. And so in the case when it's completely contained, then the contribution to the metric is that normalized volume of intersection times 1 plus what is now the minimum distance. And so again, that minimum distance, that 1 plus the minimum distance term, gives it a gradient so that if you're just barely inside, that's better than if you're deep in the interior. So what this does is this gives us a continuous metric. And you can see, I went and I evaluated this matrix of moving these two spheres relative to one another. And over here on the right, we have the red line showing the minimum distance. And then down here, we show them, where we show them intersecting. And then down here on the left, they're on the interior and it's calculating that minimum distance. But when we combine all this together, we get this combined metric where the constraint value is this horizontal line, right? And above it is bad, is interfering, and below it is good. And, this isn't a smooth metric, right? This isn't second or third order smooth, but it is continuous. And so you have a continuous measure of it not interfering that then changes sign when it interferes and then continues on up, even no matter how far it goes on the interior. So this is the sort of the global metric that I output. And all of these different computations, I'm doing the best I can to come up with something analogous to this, right? I want to come up with, very rich data. Like over here, I calculate a bunch of things. I calculate the volume of interference. I calculate the minimum distance. I tell you the points at the endpoints of the minimum distance line. I tell you the volume of the primary and the second volume of the secondary. So I calculate a whole bunch of things, but I also try and calculate that single metric, that top level thing that captures the interference as a whole. And I try and interpret that across the board so that you can use that for your design study. But then everything's also available through the API. So if you want to drill down and really find, where does my interference happen? That information is also available. So that's external interference. And you're going to use external interference with certain kinds of auxiliary geometry. And the two examples in there right now is the arc that the propeller swings in as one, and then also the rotor burst arc. So these are geometries that are not defined independently, right? They get their definition from the parent propeller. But then we can use that as our interference check. So we can use that to say, okay, does the propeller arc interfere with the aircraft? Does the propeller arc interfere with the ground plane? Does it adjust with anything else? And it's a legitimate geom. So you could use these things in comp geom, CFD mesh if you wanted to. You can export them to step files. You can just look at them. You can visualize and see, does your model conflict? You can do all of that. You can also use it with Snap2, which is a feature that Brandon mentioned earlier. So you can use it to adjust parameters until a clearance is met. And then, of course, the reason they were added was so that we can do it with geometry analysis. So those two already exist today, but expect more of these. Again, expect more of these in the future. Don't be surprised if I don't add the rooster tail of the water put up from a landing gear, and you'll use that as a requirement that it shouldn't be ingested into the engine. Don't be surprised if I don't put in some measures of the turbine, the 1/4 or the 1/3 turbine disk burst criteria. So there's a bunch of these that are possible that I haven't had time to do yet, but expect there to be a lot more auxiliary geoms down the road. Now, that was an external analysis. You might also want to do something where you want the small sphere, to be inside the big sphere. And so this is what I call a packaging geometry analysis. So it's an internal check. And so we're going to do the same thing here. We're going to take each geometry group. We're going to take the comp geom of it, including negative geometries, and find their OML. And then I'm going to compare those two to one another. But essentially what I've done, and it's more complicated than this, but I've essentially flipped the sign on the objective function. So now what you see is this little guy is supposed to be inside the big sphere, but since it's not, now the violation is that volume outside. So before I was doing a Boolean intersection calculation, now I'm actually doing a Boolean subtraction, and I'm subtracting the big sphere from the little sphere to get the volume of interference. But I do what I did before, where I have these different cases where inside is good and I calculate the minimum distance. Interfering is bad, I calculate the volume on the outside. And if you're all the way outside, then I calculate the distance and the volume, and I do 1 plus the distance to get a continuous metric. And the same thing, I end up with this continuous metric that can be used as an optimization in a gradient and as a check when you're in a situation with internal packaging. There's also something that I call the self-external. So what this is the other external check is one group of components against another. We do comp geom, and then we compare those two groups as a whole. And so if one of them is, say, a wing and a body, and we take the OML of that, and the other is, something else, we're not checking individually against the wing and individually against the body. We're checking against that wing body combined. So another thing you can do is sometimes you might want to check the group of a set or even the multiple surfaces of a single geom. In the case of symmetry or propellers, do those interfere with themselves? So basically, does a set, without doing comp geom, but do the members of a set interfere with themselves? So here on the right, I've shown a bunch of components that you might find packaged inside a UAV. We've got a camera up here, we've got a satellite dish, we have a fuel cell, we have some radio boxes. And so, we have all of these different components that are supposed to be packaged internally. And what we would do is we'd put them in a set, that would be the internal stuff set, and then we would check, will do any of those interfere with each other? And and you can see there's a tiny little red line because the closest distance between any of these things and each other is actually that little red line right there. The other place where this comes in handy is in symmetry. So here, if we want to check, do these two auxiliary geoms of the swing of a rotor, do these two auxiliary geoms, do they conflict with each other? And again, this is one geom, they're just the left and right symmetrical copies. So do they check with each other? Or in the case of a folded prop, we want to be able to, place the fold axis and fold angles. We want to we don't want to fold it so tight that the rotor blades interfere with each other. And so these rotor blades are all part of a single propeller, in fact, of a single symmetrical copy of a propeller, but we still want to be able to check, do they interfere? So this is what we call the self-external geometry analysis. Finally, the last one that's not landing gear related that I'll talk about is the visibility, which is the from point visibility. And that may be foreshadowing. Maybe we'll do other kinds of visibility later. But what we're doing is we take a point in space, which is typically going to be the pilot's eye point, but it could also be the point of a camera or other sensor that's on your aircraft. And then we're going to calculate from that geometry, from that point, what is the field of view that's either visible, or we can calculate occluded from that point. And I'm going to calculate that as a polygon in azimuth and elevation coordinates. So I'm going to calculate that as a polygon. I'm going to calculate some other metrics like the forward visibility bounds and the over nose visibility angle. I'm also going to calculate the visibility fraction, how much of the solid angle in steradians is visible either, forward, up, and left in each octant. So we're going to do that. If you want your viewpoint to be inside the aircraft, then you need a window. You need a window to the outside. So I've added the ability to do a cutout. So you can actually specify, okay, this subsurface becomes a cutout and you can see through that. And then it's also been integrated with the human geom. So now if you place a pilot, it knows where their eye point is. And when you do this kind of analysis, it'll use that eye point as the point to start the visibility analysis from. There's a lot of fancy stuff that went into this. It's really kind of fun if you're nerdy like me. But so what I actually had to do was take that whole 3D mesh from the perspective of the viewpoint and convert it into spherical coordinates, azimuth and elevation. I drop the radius. And then I do a 2D projection, and I combine all of those different triangles in azimuth elevation to then combine to find that occluded view. And I take that union, and then I have to transfer it back into 3D. And if you've ever looked at a map of a globe and you're not a flat earther, then you know that things like the Mercator projection have lots of distortion. And so going from 3D space to azimuth elevation and back, you have to deal with this. And so I actually refined the triangles. So this picture down here on the right is a viewpoint. It's actually this case in the previous case where the eye point is above this pod with wing. And you can see, we have this occluded visibility down in front and everything like that. So this plot is actually azimuth and elevation. So here we're looking forward down the center, whereas if we go over to the right and the left, we're then looking aft. And straight ahead is basically right here in the middle. Up is in the top half and down is the bottom half. But what I've actually had to do is these are the actual triangles of that mesh. And of course, they're now curved. So I had to take the triangles and I had to refine them as I did the conversion to spherical coordinates to come up with these curved polygons here that then I took the union of to transform back. So this has been fun. Okay, so I'm going to go ahead and fire up a demo. We've got a little bit of time, and I'll try and show you some of these things as we go. And again, if anybody has any questions, go ahead and fire them off in the chat. I'll try and keep an eye on that. So I'm going to start by looking at the tilt rotor model. So this is the case that that I have many of these set up in. And so like we were talking earlier, we have this geometry analysis where, if I have each geometry checked. So this one is named cruise prop. The primary group of geometry that it's using is all the cruise non-rotating components. And the secondary group of geometry that it is the prop clearance auxiliary geometry. So if I click show only on this analysis, what that's going to do is that's going to show me, these two groups of geometries. Obviously the cruise rotating props, and also then the non-rotating parts of the airplane. So that's what we've got here is that geometry. And then you can see this is just a simple external geometry check. And so if I evaluate that, it'll do that calculation, and it calculates that minimum distance right there for me. So, we can go through each of these. I've gone through them once already, so I'm not going to belabor that. But I do think it would be fun to let's go and let's say that we were going to show all of our geometry. So that includes our occlusion surfaces there. Let's get rid of those 2 auxiliary geometries. So here's our aircraft. Let's play around a little bit and let's do some design changes. So what do we think would happen if we come in and we're doing a revision on our design so that our wingspan needs to be 10% larger times 1.1? So we made our wingspan bigger, and our prop rotor, we needed lower disk loading, right? When do we not need lower disk loading? So let's make that 20% bigger. We just made our prop bigger, and maybe I don't think that my wing needs to be swept. Let's take out the sweep. We've got 5 degrees of forward sweep. Let's take out the sweep of that wing. So now we've got a regular straight wing, and let's see, what did this do to our design? Did this do any good? Did this do any bad? So we'll just come over and we'll tell it to evaluate all of these analyses. And it's going to go through each one. It's going to apply the mode. It's going to use those sets. It's going to perform that analysis. And what we can do is if we come and we do show only on cruise prop, you can immediately see here's these red areas of interference. So here the cruise prop is now hitting the side of the fuselage, but also note that because we unswept the wing, since we unswept the wing, the propeller is now actually hitting the leading edge of the wing. And so if you ever wondered why a V-22's wing was forward swept, it might have something to do with prop strike with a flapping prop. So we've got that volume that we see there. In fact, if we really want to just look at that, we can no-show everything except for that volume, and we can really see, where that interference is happening. Okay, let's go to the second one, and we'll show only. Our cruise props still don't hit each other, so that was good news. Let's show only our stowed stuff. And we can also just look over here, right? And the positive ones are the ones that fail, and the negative ones are the ones that pass. So this is the only other one that's going to fail with these particular design changes. But if I come in and I look, I'm actually still clearing. I think I'm still clearing between the nacelle and the ducktail. Maybe, nope, they're interfering, I think. But the other place that it's interfering is right here at where the folded prop is now hitting the vertical tail. So we could actually just say no show to everything. And that shows us, again, our exact volumes of intersection. So our nacelle is hitting our ducktail just a little, and then our propeller is hitting our vertical tail. So we can, very quickly go through and see these kinds of checks. Now, someone in the chat wanted to check the propellers against a landing gear. So in this case, what I'm going to do is I'm going to add a new check. So this is going to be prop ground clearance. I'm going to add that. And here we want to do a plane distance. So this is just checking the distance between a plane in linear distance, not angle. So a linear distance between a plane and another group. And so in this case, we want to check the actually just one geometry, and that's going to be the prop clearance geometry, which is this right here. And then the plane, I could either go, and if I had this model doesn't have landing gear, so I could either go and put in a landing gear and either use that nominal or off nominal landing gear, or for the simplest case, I can just specify a Z plane. And right now it doesn't draw it, but so I can just come in here and I can put in a Z plane, which just so I can have something to visualize, I'm going to go ahead and put in a blank. And so let me see, where is that blank right there? And I want to see, how, in terms of the scale of my model, okay, so that's about where the landing gear would be, maybe a bit higher than that. So let's say the landing gear is right about there at, let's just call it for round numbers, minus 70. And so I'm going to put my gear at minus 70. And this is just a ground plane. Again, I don't even need a full landing gear model here, but let's just evaluate that check. And sure enough, we can see that the propellers in their arc are going to hit the ground on a V-22. And that's why it doesn't land with the propellers in the cruise position. The best it can do is about 45 degrees on those nacelles. So that's that check. Let me go ahead and let me show the pilot vision stuff a little bit. So that one was over on the transport model. And we'll come in and we can do the same sort of thing. So here's our pilot, and we're really this time only interested in the pilot visibility. So let me show only those components. So again, this is the airframe and the pilot. And in this case, we're pulling the visibility from their eye point. Now, when we do pilot visibility, we have different choices, right? If I didn't want to use a single point, a pilot, what I would do is I could just specify an XYZ point. So I can specify any point around the aircraft. So they're somewhere in the middle. But for example, let's say I had a camera that was right up here, and I could do that visibility calculation. And what you see is, and we're showing what is visible, right? We could show what's occluded. So we choose our sign convention. But from that point above the aircraft, that is the dome of everything that's visible, right? And that shows, what's visible and what's not in all directions. So that's from a point. I could also come in and I could base it off of some other component. So I could have a model of a sensor, and what it's going to do is it's going to pull that coordinate from that sensor. Now it's always going to pick it from the origin of the sensor. I didn't want to put the full complexity of attachment in here. And so if you want to specify a point on a geometry that's not the origin of that geometry, then just attach a blank to that geometry and then use that blank for the vision point. But what we're more interested in here is using the pilot. And so let's do that analysis. We'll just reevaluate real quick. And you can see we've used that pilot's vision, that pilot eye point as the origin, and we're showing what is visible. And what we've done is right here is we've shown the cutouts. So this model had 3 subsurfaces. It has the left window, the right window, and then there's a subsurface somewhere on the nacelles. And so in this list, we choose which things to cut out. So let's say we only want to look at the visibility through the left window, right? I'll just turn off the right window and then I'll evaluate, and we only get the one window. We don't cut it out. And so that allows us to go through and do these visibility kinds of calculations. I'm going to stop there and see if there's any questions. I do think that the frozen chicken test through the engine would be hilarious. Yeah, I think I'm glad to see you guys are as excited about these features as I am.
All right, thanks, Rob. Let's see, anybody pops up and has a question in the chat while we get switched over and Max can start sharing his screen.
Okay.
Let's see. Rob, do you want to address AJ's question there in the
Yep.
chat?
Yeah, I got it.
Okay. All right. Well, it's about 4:30 Eastern here. We'll go ahead and get the rest of our workshop for day 2 here closed out with Max Lindstrom from M4 Engineering. So Max, you are welcome to go ahead.
All right, sounds good. So hi, everyone. My name is Max Lindstrom, and I've been working with Rob and the rest of the M4 team here on the recent developments of OpenVSP. So I'm just going to go through a couple demonstrations just on some of the new features and how we incorporate those. So this is kind of the agenda. So the two main things that we're going to be covering is we developed an automated wing layout tool that utilizes some or the attributes from OpenVSP, and then I'm going to be showing an optimization setup that utilizes a lot of the new features that we've included as well. And before I start here, I just want to thank the Navy for funding all these recent developments, as Tim has mentioned before. So as I mentioned, to demonstrate OpenVSP attributes, we developed a automated wing layout tool, which uses those attributes to create or update wing components for an M4 Structure Studio vehicle model. And I'll talk a little more about M4 Structure Studio just in a minute here. And so this is available through the GUI and then API as well. And then after the vehicle model of the wing is set up, a finite element model can be generated using some other tools in M4 Structure Studio. And then this works for any wing-like component of OpenVSP. So, if you have a vertical tail, horizontal tail, your regular wing. And then usually, this process of fully setting up a wing can take a couple of hours when it's done manually, but this tool allows you to set up a wing in about, 20 minutes, depending on how complex your attributes are going to be, and allows you to run automated studies that can further speed up that development process for you. And so since I'm talking about the automated wing layout tool, I just want to give this quick overview of M4 Structure Studio. So the goal of M4 Structure Studio is to predict structural weight for unconventional vehicle designs, especially when there's not much history. And then this requires the ability to predict structural sizing, which has a lot of depends on inside of it. And so determining these depends on items is very time consuming and difficult with the conventional processes, but with M4 Structure Studio, we can automate those processes. And so this represents, about 20 years of tackling this problem. And then what this allows us to do as well is integrate with parametric geometry tools such as OpenVSP to really accelerate that process. And so this is just showing an example of going from OpenVSP to structural finite element model. And so we're using M4 Structure Studio to, again, automate that process. So just going from that parameterized geometry in OpenVSP to go all the way to the FEM. And this is just really showing, that power of M4 Structure Studio to automate the process for us here. And then also with M4 Structure Studio, we can visualize the results as well, such as flutters, you can see in the left image here, and stresses and strains, which are shown on the right. So now with that overview done, I'm going to dive back into the wing layout tool itself. And so I just want to give an overview of the attributes used to set up the model. I'm not going to go through the exhaustive list that we use to set up this model, but just kind of an overview. So the material attributes, you can use two possible materials, so isotropic or orthotropic, and then this as well as the property regions are set up at the vehicle level. And with the property regions, you're able to do shell, laminate, shell, and beam. And then the big ones are the structural layout attributes. And what these are allowing you to do is to define the structural layout. You can place property regions and you set the meshing parameters. And then these are actually defined at the wing component level. And so this is just kind of giving an example of a material setup. So, in this case, it's just setting up an ice chalk material. So you have a materials attribute group, which is kind of grouping all the materials together. And then inside the attribute group, you have attribute groups of materials. So in this case, material 1, material 2, and so on. And then you define inside of there your actual attributes that define that material. And so in this case, we're using doubles and integers. Material ID is an integer, density, shear modulus, Poisson's ratio, Young's modulus, that kind of stuff. And so to kind of showcase this tool, what we're going to do is we're going to run a static aeroelastic based design optimization, specifically wing weight optimization. This model is an electric general aviation aircraft. It has a predefined fuselage, H-tail, and V-tail components. And then that wing component is going to be laid out using the OpenVSP attributes and the wing layout tool. And then what we're going to do is just increase the number of ribs each iteration. And I'll kind of show that process in a second here. And then running the analysis, it's just going to be a single stress constrained static aeroelastic analysis. And it's just going to be undergoing a pull-up maneuver. And so this is just showing our model here. On the left side, you can see the OpenVSP model. On the upper right, that's an example of the finite element model with one of the wing configurations. And then on the lower right there, it's just showing the wing being deflected under the static aeroelastic analysis. And so this just kind of goes over the process that we're doing here. So to perform the parameter sweep, what we need to do is first, create those initial attributes, and then we also have to set a desired ADA value for the hinge locations for the flap hinges and the aileron hinges. And this is just so that downstream we can make sure those flap and ailerons are kind of staying around the same location. And so after the setup, we run the automated wing layout tool. This usually takes 1 to 5 seconds. It's pretty fast. And then after that, we run the Infrastructure Studio FEM merge. So that's just generating the FEM. And that can take about 30 seconds to a minute, sometimes longer, just depending on how complex your model is. And then we run the optimization through MSC Nastran, run our weight report, and then we're going to increase the ribs and just change those the flap and aileron hinge locations based on the new rib layout. And so this is just showing the different layouts here. So it's increased number of ribs by 1. It does 1 on each side, and the finite element model is being shown in the GIF here, and you can see those regions they're empty, where it's kind of cutting off the end of that rib there. That's where the control surfaces are being set up. And then after the optimization has been run, these are the results here. So it's just showing the results for the skin thickness and the ply X strain. And so the skin thickness near the root increased to minimize that total weight. And all these skins were initially started with a total thickness of about 0.44 inches. And as you can see, as number of ribs increased, the thickness closer to the root increased as well. And that's just, you can see on the left GIF here with that same scale going up. And then the distinct property regions, you can see in the GIF on the right here, just showing the strain. And so you're able to see those regions kind of where it looks kind of discontinuous in there. And so this was just, showing a demonstration of how attributes can be used in downstream analysis tools such as Infrastructure Studio. And you can really see the power of using attributes for this to automate your processes and just really streamline everything for you. So now I'll move into the optimization setup that we did with all the new OpenVSP features. In this case, we're going to look at mostly, or was featured inside of here. We're going to look at modes. So we used modes we use a folded mode, a cruise mode, and a hover mode. We kind of saw those as Rob's been showing the different models with MV22. So the folded mode is going to be used for a boundary box component. The cruise mode is going to be used for VSPRO and an interference component. And hover mode is going to be used for the tip back and tail strike analysis, just so that we don't have the propeller interfering with the ground plane there. And then one thing actually came up with as we were setting up these demonstrations is it'd be really nice to have a geom set bounding box. So that got utilized in here as well. So it's just so we can exclude that propeller interference geometry for the bounding box constraints. And then auxiliary geometries, like Rob has talked about. In this case, we're looking at propeller interference geometry and a 2-point plane geometry, which is going to be used to represent the rotation about the main gear for calculating that tip back and tail strike angle. The interference analysis, so propeller interference with other geomes in the vehicle, and then also self-interference analysis, so that's the propeller self-interference, and then a tip back and tail strike, and then just adding that landing gear in there that Rob has just talked about. So this is the model we're using. It's similar to the one that Rob's been showing. So it's based in MV22. The initial geometry here is it has a fuselage of about 57.33 feet, rotor diameter about 38 feet. And then our masses inside this model, the wing structure is going to be a dependent variable. The fuel is being included as design variable, and I'll go over more of that in the next slide. And then propulsion systems, so the big rotors and everything there has been added as point masses on the tips of the wings. And so this is just going over the optimization setup. So we're going to be using 2 different angles of attack. So one for cruise, one for maneuver. We're going to be having wingspan, wing sweep, wing tilt, dihedral, fuel weight, and then a main gear X position, and then the relative Z location for the landing gear. And we can kind of see how those are going to change based on the results here. And then as constraints, what we're going to have is we want lift equals weight for the cruise and the maneuver. In this case, the maneuver is going to be a 2G pull-up, essentially. And then we want our range to be greater than 2,000 miles. And we want our bounding box just to be within those lengths that are specified there. We're just looking at the Z length and X length in this case. And then for the interference checks, we have the cruise prop. We have the proper self-interference, and then we're also going to be checking that stowed interference as well to make sure we're not hitting anything. The reason the cruise prop is between -12 and -1 is just because we don't want it to be sweeping too far forward. We kind of wanted to keep it within a certain region there. And then for the tip back and tail strike, we wanted that to be around 15 degrees, plus or minus 0.1. And this is kind of it's the XDSM diagram for the optimization. So you can see our main components here. So we have a loads component, which mainly is for running VSPRO, and then structures component that takes the VSPRO and turns it into a weight for the wing, and then we calculate total weight based on the wing fuel and the wing mass, and any other mass that we have included. Fuel range, we're calculating. We're also doing that lift equals weight, and then we're just doing the separate checks for the bounding box, interference checks, and that tip back and tail strike. And I can talk more about some of these specific components at the end if we have time here, if you're curious. But I did want to talk about specifically the components that take into account the new additions to OpenVSP. So in this case, we're looking at that bounding box constraint. And so what it's doing here is going to fold the VSP model based on the mode for packaging, and then it gets the bounding box lengths from that. And so the inputs for this are, those design variables that we're changing, and it's outputting the X, Y, and Z lengths of that bounding box. And so just to show the preliminary results of this, you can see that it keeps the wing much tighter there, and whereas the non-bounding box, you can see it's increasing that wingspan to decrease the drag there. And then for the geometry analysis constraints, basically what these do is it obtains the analysis metric for a given geometry analysis in the VSP model. In this case, I talked about there are several different geometry analysis that we're doing in here. And so it's taking the inputs that are, for the overall model. So that's the span, root chord, taper, sweep, dihedral, and then there's some other parameter specific to the geometry analysis as well. And I just wanted to mention, so I mentioned wing tilt as a design variable. So that's in this case just showing there's a pivot point here, just how what the angle is between that pivot point for the wing there when it's folded. So yeah, so that's geometry analysis metric. And so this again is just showing some preliminary results. So we just increased that propeller wobble. And as you can see, it swept that wing forward. And just like Rob said, that's probably why the MV22 has a forward side wing, is to make sure that propeller doesn't interfere with the wing there. And if you look at the tip back results, obviously, with MV22 or like this vertical takeoff and landing model, you're not necessarily worrying about tip back and tail strike as much, but just to demonstrate, the capabilities that this has, we did that analysis in here. And so you can see that the tip back angle met the constraint, and that the X position shifted forward a little bit, and the relative Z location shifted down a little bit to meet that constraint. And then once again here with the tail strike, similar thing. It met the constraint, and then X shifted forward, Z shifted down. So obviously these run the same model, so we're going to end up with the same X point, X position, and the relative Z location here. And it's just kind of showing the overall results for the full model. I'm not going to go through every little one here, but you can see on the left-hand side there, it's just a GIF showing the how the model is changing over time. And then one on the right is the finished or optimized, model, if you want to call it that. And then I just want to mention, so this GIF creation, and I think Thomas is going to talk about this tomorrow, was created utilizing OpenVSP facade to visualize the design changes in real time. And so basically after design changes were made at the beginning of each iteration, a screenshot was taken of the OpenVSP graphics window using the API with the facade. And with that, I'm open to taking any questions here.
Thanks a ton, Max. I'd like to hammer one thing home while we wait for any questions to come up. If you'd back up to the tail strike slide that you had, and I just wanted to point out to everybody, this is an example of what I was talking about earlier, where in the design case on the left, the minimum angle tail strike is there on the base of the fuselage, whereas on the right, it's on the lower extension of that vertical tail. And so, if you were trying to, a human sees this immediately and is able to do the construction, to find that line and to do that. But if you were trying to automate this in CAD or in other tools, it's not trivial to just, take a point and draw a line. You've got to do a search in order to find that point. And this is a perfect case where when you do a design study, what that point is very likely going to change as your geometry changes. And I just wanted to capture that in this figure.
Yeah, thanks, Rob.
Yeah, no problem.
I haven't seen any additional questions pop up in the chat. We still have about 10 minutes or so before the end of the day. And if anybody had any requests for some simple demonstrations or showcase a feature that we haven't talked about yet or isn't already on the schedule tomorrow, we might be able to do a quick demonstration of that. Otherwise, we might get 10 minutes of our day back. All right, well, still not seeing any requests come in, so I think it was another successful day here for the VSP workshop. Thanks again, Max, for showcasing some of that content and showing how everything here is tying together. It was really interesting to see it all in action.
Of course. Happy to do it.
All right. Let's see. We've got somebody asking if it's possible to make the example available with the new release. So
yeah, I will upload the transport and the tilt rotor examples that I've been showing to the VSP Air Show when the release is out there for them to be. The example that Max did uses a lot of infrastructure, both M4SS and also I think you used OpenMDAO. And so I don't think that there's a lot of value in posting that online for everybody, but I'm also sure that if you're interested in becoming a M4SS customer and you contact M4, that they'll be happy to share that example with you. Yes, M4SS is a commercial tool that M4 develops and sells to do, the whole structural life cycle. It can be used with OpenVSP, which is a great capability, but it can also be used independently or with other geometry tools. And so that's a capability that M4 has developed and that they work with their customers on. There is some OpenVSP structures capability that we have a long track on tomorrow. Pros and cons compared to M4SS, but M4SS is a really mature tool, and M4 has a lot of expertise applying it for clients. Okay, I think that's probably it.
sounds good. We will see everybody tomorrow for the final day.
Thanks, Max.
Of course.